Hello there, welcome to Just About Space. Close your eyes, though not so tightly that you start to notice the little dancing sparks behind your eyelids, and imagine everything you have ever known, every atom of you, and every photon that has ever brushed your skin, not simply destroyed, not drifting in some dark cosmic ruin, but never having been at all. Imagine a place, or perhaps not even a place, where there is no space, no time, no light, no darkness, no before or after. A realm that laughs in the face of your tidy timelines, because timelines only make sense once you have time to put them on. Physicists call it before the Big Bang, though before is a cheat. Before implies a clock. Before implies something waiting for its turn. But when you look at the Big Bang in the way cosmologists do, time itself was born with it. And so the question becomes something more subtle, more unsettling. Not what happened before, but what could possibly exist when before isn't even real yet. You'll hear ideas wild, elegant, and deeply human. A quantum foam bubbling with infinite beginnings. A cosmic cycle endlessly collapsing and exploding like a chest rising and falling in eternal breath. A multiverse in which our own Big Bang is just one bubble in an endless froth of newborn universes. Or maybe nothing at all, and the nothingness is so perfect, so total, that it defies even the concept of nothingness. Over the next hours, we'll drift through these theories, not to answer the question outright, but to loosen its grip on you. By the time we're done, you may feel that what was there before the Big Bang is less of a puzzle to be solved, and more of an ocean you simply float in. You'll carry the weight of it, the vastness of it, in the quiet space between heartbeats, and maybe, if you're lucky, you'll fall asleep before you notice just how infinite the question really is. You've been taught to trust before since you were a child. Before breakfast comes waking up. Before the rain comes the clouds. Before the story begins, the pages are blank. It's one of the most basic human instincts, placing events on a line from left to right, from then to now. It's so embedded in you that you can't imagine it being wrong. But in cosmology, before is not a reliable narrator. Imagine you're holding a clock, a solid, ticking thing. It doesn't matter if it's a glowing red digital display or an old brass pocket watch with a heartbeat for a second hand. Either way, it's your anchor. Now imagine the clock isn't broken, but meaningless. The tick doesn't lead to a tock, because there's no framework for next. The hands may be frozen, or they may not exist at all. This is the problem you run into when you ask what was there before the Big Bang. When physicists say time began at the Big Bang, they're not being poetic. They're stating that the mathematical description of time, its geometry, its direction, even its possibility, comes into being with the expansion of space itself. You could say time is stitched into space, and before the stitch began, there was no thread to follow. Asking what came before is like asking, what's north of the North Pole? The question seems clever until you realize it has no physical footing. Still, our brains refuse to give up the chase. We imagine a kind of backstage to the universe, a dark corridor behind the curtain of the Big Bang where something or someone must have been setting the stage. Even the most disciplined cosmologists who can recite the equations of general relativity in their sleep often admit in private that they feel the pull of the question. The human mind doesn't like edges without something on the other side. Einstein's equations themselves tell a strange story here. If you roll the clock backward in those equations, the universe shrinks, contracts, and heats until the numbers begin to misbehave. Press further, and the equations spit out infinities, temperatures that make no physical sense, densities that become absurd. This singularity, the mathematical cliff edge, is where our best theories fail us. And so before becomes not only a philosophical hazard, but a mathematical dead end. This is where people split into camps. Some say the singularity is a real feature of nature, an actual boundary to time and space beyond which there is simply nothing. Others argue that the singularity is just a signal that our current physics is incomplete, that there must be a deeper theory smoothing over that cliff, revealing not an end but a doorway. In the early 1980s, physicists like Stephen Hawking began to play with radical ideas about this. What if time didn't simply extend backward in a straight line, but curved like the surface of the Earth? What if, in the earliest moments, time and space blended so completely that before the Big Bang wasn't a meaningful phrase, not because nothing happened, but because before stopped being a concept you could apply? Hawking's no-boundary proposal was one such attempt to dissolve the question, not by answering it, but by proving that the question itself doesn't fit the shape of reality. But there's a discomfort in that, isn't there? It feels like being told there's no treasure, just because the map is wrong. And yet, this is where cosmology forces you to let go of your usual tools. The comfort of before is stripped away, leaving you with a strange new landscape where beginnings might not need to begin. For you lying here listening, the problem with before is almost a kindness. If before is meaningless, then so is the anxiety of trying to picture it. There's no cosmic ledger you've failed to read, no secret moment you've missed. The universe is not hiding its diary from you. It simply hasn't written those pages, because pages are a thing that came into existence with the book itself. As we move deeper into this journey, keep that in mind. You are trying to follow a path into a forest that didn't exist until you took your first step, and yet you walk on. Picture the universe as a film you can rewind. At first, the motion slows. The galaxies draw closer together, stars crowd the screen, everything heating, brightening. You keep going. Galaxies collapse into a shimmering haze. Planets, stars, atoms all dissolve into pure plasma. You rewind further still, past any structure, into a chaos of energy so dense that the very concept of particle becomes meaningless. And then, you hit the wall. It's not a visible wall. No sheet of glass hanging in the void. It's a wall made of numbers, and those numbers have gone bad. The calculations that describe the universe, Einstein's general relativity for gravity, quantum mechanics for the subatomic, both refuse to play. General relativity tells you that the universe's size is shrinking towards zero, its density skyrocketing toward infinity, and its temperature climbing to values so high that high no longer means anything. Quantum mechanics, normally your escape hatch for such extremes, simply shrugs, as if to say, you're asking questions I have no business answering. This is the singularity problem, the point where the known laws of physics break, not bend, not blur, break. Physicists are uncomfortable with infinities. Infinity in math is fine. It's an abstract playground, but infinity in physics is like a red, blinking error message. It means your model has wandered into territory it wasn't built to navigate. The singularity at the start of the Big Bang is one such error. It's not proof that the universe began from an actual point of infinite density. It's proof that our current theories stop working when we try to describe such a point. And here's the twist. The singularity is not unique to the Big Bang. You find them in black holes too. If you cross a black hole's event horizon in the math, you meet the same sort of infinity mass packed into zero volume, curvature of space-time bending without limit. But many physicists believe black hole singularities are also just warnings. Get a better theory. This one's out of its depth. That better theory is what people call quantum gravity. A unification of the laws that govern the very large with those that govern the very small. We don't have it yet, though there are candidates. String theory, loop quantum gravity, causal dynamical triangulations. They differ wildly, but they share one hope that when quantum gravity is understood, the singularity will dissolve into something finite and comprehensible. Some imagine the singularity replaced by a kind of bounce, a moment when the universe, instead of collapsing into nothing, rebounds from a prior state, like a ball hitting the ground. In these models, the Big Bang isn't a beginning but a handoff from a universe that was contracting before ours began to expand. Others imagine the singularity smoothed into a foam of quantum fluctuations, a jittery haze of possibilities where space and time themselves are not yet fixed, where the seeds of the universe tremble before they sprout. The trouble is, we can't see past the first fractions of a second after the Big Bang. Our cosmic vision is fogged by the universe's own early light, a searing brightness that only cleared after 380,000 years, when atoms first formed and the cosmic microwave background began its quiet hum. Before that, we are detectives without a crime scene, relying on hints on the shape of the expansion, on the faint fingerprints left in the microwave glow. And so the singularity remains a riddle written in the margins of the universe, one we can read only up to the point where the ink blurs into nonsense. It's a frustration, but also a freedom. Without a clear picture of t=0, we're left with a playground of theories, from bouncing cosmologies to endless cycles to spontaneous quantum births. For you, lying here, perhaps it's easier to think of the singularity not as a wall, but as a horizon. Beyond it may be more universe, or no universe, or something that doesn't even deserve the word thing. Whatever it is, it's the place where every known law we cling to takes a polite bow and steps off the stage, leaving the curtain to sway in a wind we can't yet measure. Imagine a stage so dark and so silent that it cannot even be called a stage. No backdrop, no actors, no light above or floor below. And then without warning, without plan, a spark. In quantum mechanics, this kind of sudden appearance isn't as outlandish as it sounds. At the smallest scales, nothing is never truly nothing. Even in what we call a vacuum, particles and antiparticles flicker into existence, live for the briefest possible heartbeat, and vanish again. This restless dance is known as quantum fluctuation, and it's one of the strangest, most counterintuitive features of the quantum world. It means that emptiness is never still. It's always buzzing, always seething. Some physicists think the same principle could scale up. They imagine that our entire universe might have been one such fluctuation, an absurdly lucky, self-sustaining one that didn't just wink out after a split second, but expanded into the cosmos we know. This is sometimes called the universe from nothing scenario, though. It's not really nothing at all. It's a kind of quantum nothing, which is still a something, just a something without space, without time, without form. If you want to picture it, imagine a frothing ocean of potential, with bubbles forming and collapsing constantly. Most bubbles collapse instantly, leaving no trace, but one bubble grows instead of shrinking. Its surface swells, its inside fills with the ingredients for stars, galaxies, and you. That bubble is our universe. And that ocean? It might still be there, invisible and unreachable, birthing other bubbles even now. This is where quantum theory and cosmology start to blend into something almost mythological. If universes can pop into being from quantum fluctuations, then before the Big Bang might simply be a realm where universes are as ordinary as raindrops. We'd just happen to live inside one that lasted long enough for us to ask the question. Of course, there's a catch. The kind of quantum nothing that could give birth to a universe isn't the same as the nothing you imagine when you close your eyes. It's not an empty box. It's more like the rules of the game without the board or the pieces. The laws of physics, whatever their deepest form is, would have to exist already, ready to allow such a fluctuation. And that leads to another unsettling question. If those laws existed before our universe, what kind of reality did they inhabit? Some thinkers dodge this by saying the laws of physics are the reality. There's no deeper layer, just the potential for universes, forever humming beneath the surface. In this view, the Big Bang wasn't a one-off miracle. It was just one lucky roll of the cosmic dice. Others lean into the weirdness. If quantum fluctuations can birth universes, maybe they do so endlessly. Perhaps each new universe has its own physical constants, its own laws, its own version of reality. Ours just happens to have the kind of chemistry and gravity that allows stars to form and life to arise. This is sometimes called the multiverse, though that's a word that tends to open more cans of worms than it closes. For you, listening in the dark, This idea can feel oddly soothing. It suggests that the origin of the universe wasn't a singular miracle perched on the edge of nothingness, but part of a natural process. A process that might be happening everywhere all the time beyond the thin membrane of our observable sky. You, your thoughts, your heartbeat, all might be the product of a tiny ripple in an ocean that never sleeps. And if that's true, then the question, what was there before the Big Bang, has an answer that is less like a wall and more like an infinite field, one where beginnings and endings happen constantly, everywhere, forever. You just happen to wake up inside one. You might be used to thinking of the universe as a singular event, a single cosmic firework that bloomed once long ago, and is still drifting outward in silence. That's the way the story is often told. One Big Bang, one beginning, one arrow of time. But imagine something different. Imagine instead that the Big Bang wasn't a lone explosion, but one spark in an infinite chain of sparks. Imagine that beyond the boundary of everything you can see, beyond the deep curtain of space-time itself, there is a vast field, featureless, endless and restless, where the process that gave birth to our universe is still going on. Not in the past, not in the future, but now, always. This is the idea behind eternal inflation, a burst that never ends. To understand eternal inflation, you first have to understand plain old inflation. In the early 1980s, physicists like Alan Guth, Andre Linde, and others noticed a few peculiarities about the cosmos that standard Big Bang theory couldn't explain. For one, the universe is astonishingly uniform in every direction. The cosmic microwave background, the leftover light from the Big Bang, has almost the same temperature no matter where you look. This smoothness was puzzling, because regions on opposite sides of the sky are so far apart, they should never have been in contact, never had time to agree on a common temperature. Inflation theory fixed this by proposing that in the first tiny fraction of a second after the Big Bang, around 100 seconds, space itself expanded faster than the speed of light. This doesn't break Einstein's rules because it's space stretching, not objects moving through space. Inflation was like blowing up a balloon in one sudden, impossibly fast breath, smoothing out any lumps or irregularities before letting it slow into the more leisurely expansion we see today. The result? A cosmos that looks smooth and uniform on large scales, but still has tiny fluctuations, the seeds of galaxies that quantum physics predicts. And indeed, the cosmic microwave background shows exactly those tiny temperature variations. Inflation works. It fits. But eternal inflation takes this seed of an idea and plants it in infinity. Bubbles in the field. In the eternal inflation model, inflation doesn't stop everywhere at once. Instead, think of space as a field that can exist in different energy states. Most of the field is stuck in a high energy state, which causes space to expand exponentially. But in some regions, the field decays into a lower energy state, and inflation ends there. When that happens, the energy from inflation gets dumped into a burst of matter and radiation, a local Big Bang. That local bubble stops inflating inside itself and evolves into a universe like ours. But the rest of the field, the regions still in the high energy state, keep inflating. And inside that still inflating space, new bubbles form. And in those bubbles, inflation ends locally, producing their Big Bangs. If you could step outside our universe and look at the whole process from some impossible vantage point, you might see an endless frothing bubbles swelling into universes surrounded by a sea of inflating space-time. It's not a single firework, but a field of fireworks, each one its own cosmos, a landscape of possibilities. What makes eternal inflation especially strange is that each bubble universe can, in principle, have its own physical constants. The rules that govern matter, energy, and even time might differ from bubble to bubble. In some, stars might never form. In others, gravity could be so strong that the whole universe collapses before life has a chance. There might be universes where atoms themselves are impossible. And then, among all these, there is ours, a universe with just the right mix of constants for stars to shine, planets to form, and for you to be here, lying in the dark, listening to this. This is where some physicists bring in the anthropic principle, the idea that we find ourselves in a universe that permits life simply because, well, if it didn't, we wouldn't be here to notice. Before the Bang, in this view, asking what was there before the Big Bang is a bit like asking what's outside my hometown. The answer is more land, more terrain, more reality. Before our Big Bang, there was inflating space, cold, empty yet full of potential. And in that space, other universes were already being born. There's no moment zero in the eternal inflation picture, no single point where everything began. The process is, as the name says, eternal. It has always been happening, and will always be happening, somewhere. The Big Bang becomes not the beginning, but a beginning, a local event in a much larger, unending story. A universe we shall never see. The beauty and the frustration of eternal inflation is that we can't see beyond our own bubble. The edge of our observable universe is a horizon we can't cross. Not physically, not even with light, because the space between us and everything else is expanding too fast. Anything beyond that horizon is lost to us forever. That means eternal inflation can never be confirmed by direct observation. We might find indirect evidence, patterns in the cosmic microwave background, signs of bubble collisions, subtle fingerprints of inflation's mechanics, but the vast majority of this multiverse will remain a mystery. Our bubble is sealed, and the others drift beyond our reach. A sleep-friendly infinity. And yet, there's something almost soothing in this idea. If eternal inflation is true, then the universe is not fragile. It doesn't balance on a single lucky event in the distant past. It is part of a constant, ongoing process. A process that doesn't need a start or an end, only change. The cosmos becomes less like a single candle burning down, and more like a starry sky where new lights are always being born, even as others fade. And somewhere out there, forever hidden, are universes with their own skies, their own stories, their own beings lying awake, wondering if they are alone. In eternal inflation, our Big Bang is just a room in an infinite house. We will never walk its halls, never visit the other rooms. But knowing they're there, knowing we are part of something that vast, can make our own walls feel both smaller and more precious. Picture yourself standing on a shore. The waves roll in, one after another. You watch them crash, retreat, then return. The ocean does not keep track of how many there have been. The waves have no memory. There is no first wave. Now imagine that the universe might work the same way. The rhythm of everything. The cyclic universe idea is, in some sense, one of the oldest cosmological models we have. Ancient myths often imagined creation not as a single moment, but as a rhythm, a breathing, a pulsing, a birth and death repeated over and over without end. Modern cosmology has found ways to turn that poetry into physics. In the cyclic or bouncing universe models, the Big Bang wasn't the one and only beginning of everything. It was simply the latest crest in an eternal pattern. The universe expands, slows, contracts, and then bounces back in another expansion, over and over. No beginning, no final end, only cycles. The problem they set, solving. Why imagine cycles at all? Well, it's partly because of the singularity problem we've already explored. If the universe really began from an infinitely dense point, our physics hits a wall. But if there was a previous phase, a contracting universe that collapsed to a small but finite size before bouncing back, then maybe we can avoid the singularity altogether. Cyclic models also offer a potential solution to the mystery of time's arrow. In each cycle, entropy, the measure of disorder, might reset or be diluted in some way. This would allow the universe to start fresh each time, without becoming a cold, featureless soup after a few trillion years. ekpyrotic universes and brain collisions. One of the more exotic versions of the cyclic idea comes from string theory and something called M-theory. In this view, our universe is like a three-dimensional brain, short for membrane, floating in a higher dimensional space. There could be other brains parallel to ours, and every so often, on timescales of perhaps trillions of years, two brains collide. That collision releases an enormous amount of energy, producing what looks from inside the brain like a big bang. After the collision, the brains move apart, the universe expands, and eventually they drift back toward each other for the next collision. Each impact is a new cycle, a new burst of creation. In this scenario, before the Big Bang isn't nothing. It's an entire contracting universe on a collision course with another. The cosmic bounce without brains. You don't have to believe in extra dimensions to have a bounce. In some quantum gravity models, the equations that describe space-time actually reverse when densities and energies get too high. Instead of collapsing into a singularity, the universe reaches a minimum size and then begins expanding again. It's like a ball dropping toward the ground, not smashing into it and stopping, but rebounding upward in a smooth arc. This idea has a certain elegance, because it reuses the same physics we already know, just extended into extreme regimes. Space-time becomes elastic, and the Big Bang becomes the rebound point in an infinite sequence of expansions and contractions. Evidence? That sips the hard part. If the universe is cyclic, we should, in theory, be able to find traces of previous cycles. These could be subtle patterns in the cosmic microwave background, tiny irregularities that might have survived from a past universe. Some researchers have claimed hints of such evidence, though nothing has been confirmed. The problem is that each bounce, if violent enough, would erase most of the memory of what came before. The early moments after each bounce are dominated by the same smoothing processes as standard inflation, which tend to wipe the slate clean. That means if we are in a cyclic universe, we might be living in a story where all earlier chapters have been neatly torn out. The philosophy of endless returns. There's something quietly radical about a cyclic universe. It denies the notion of a final answer. There is no first cause to track down, no singular moment when the lights went on for the first time. It's not a puzzle with a neat corner piece. It's a repeating pattern woven into the fabric of reality. The ancient Greeks had a word for this kind of eternal return, palingenesis. In Hindu cosmology too, there's the concept of endless creation and destruction, Brahma creating the universe, Vishnu sustaining it, Shiva dissolving it, and then the cycle beginning again. Modern physics, in its own stripped-down way, is circling back to something similar. If eternal inflation imagines infinite space with countless universes, cyclic models imagine infinite time within one universe, our own breathing in and out forever. The human scale of it. It's easy to get lost in the math of bounces and cycles, but on a human scale, this idea is strangely comforting. If cycles are real, then we live in a universe that is never truly young or old. It is always somewhere in the middle of a breath. Our entire history, from the first single-celled organisms to you lying here now, is a single ripple on a tide that has been moving forever. And in a way that makes the present moment feel more precious, not less. We're not at the fragile beginning of something that could be snuffed out at any time. We're part of a rhythm that will carry on long after we're gone, long after our sun burns out, long after galaxies fade. The bounce is an answer to before. If you accept the cyclic model, then before the Big Bang is simply another universe, another version of this one. It may not have been identical. Constants could shift, patterns could change, but it was still a universe, still full of stars and galaxies, maybe even life. And before that, another, and another, an infinite hall of mirrors stretching in both directions through time. That's a kind of immortality, not for you, not for me, but for the cosmos itself. Section 6. The multiverse as an answer to before. If you've ever looked at the night sky and thought, this can't be all there is, you're in good company. The multiverse idea takes that quiet suspicion and turns it into a full-blown cosmological framework. It says, yes, there's more, much more. Not just more stars, not just more galaxies, but more universes. Entire realities separate from ours, each with its own laws, its own physics, its own possible histories. And if that's true, then asking what was there before the Big Bang might be like asking what's outside my neighborhood. The answer is another neighborhood, and another, and another, in every direction, without end. The many ways a multiverse could exist. The word multiverse isn't one theory. It's a catch-all for a family of ideas, each with its own path to a cosmos of many universes. One branch is the eternal inflation multiverse, which we've already touched on. In that model, our universe is just one bubble in an ever-expanding sea of inflating space-time. Other bubbles form elsewhere, each creating its own Big Bang. Another branch comes from quantum mechanics, specifically the many worlds interpretation. In this view, every quantum event that can happen does happen, branching reality into parallel versions. You choose tea instead of coffee, and somewhere, another version of you chooses coffee. At the cosmic scale, every quantum fluctuation in the early universe spawns its own branch of reality, each with its own outcome. Then there's the string theory landscape. String theory predicts an enormous number of possible stable configurations for the fundamental fields and constants of nature. Numbers so large they make astronomical feel too small a word. Each configuration could correspond to a separate universe. The landscape is this vast range of possibilities, and the multiverse is the collection of universes where each is realized. The multiverse, as a before. If a multiverse exists, then before the Big Bang is no longer a blank, it's simply the rest of the multiverse. The other universe is already out there before ours began. Our Big Bang becomes a local event, one of many, with no claim to being the first. This doesn't make the question go away, of course. You could still ask, where did the whole multiverse come from? But it shifts the mystery. Instead of hunting for the moment our universe began, you're trying to understand the rules that generate universes at all. Infinite variety. The multiverse also changes how you think about the odds. Our universe is physical constants. The strength of gravity, the charge of the electron, the speed of light are balanced in such a way that stars, planets, and life can exist. In a single universe picture, that looks suspiciously lucky, but in a multiverse, luck is inevitable somewhere. If there are countless universes, each with different constants, then it's no surprise that one of them, ours, has just the right mix for life to evolve and wonder about its origins. Some scientists embrace this as an explanation. Others reject it, arguing that it's too convenient, too unfalsifiable. After all, if you can always say, well, in another universe it's different, how do you test the idea? Can we ever see it? Here's the frustrating part. If other universes are truly separate, with their own space-time, we can't directly see or visit them. They're sealed off by horizons we can never cross. In some speculative scenarios, universes might occasionally bump into each other, leaving faint imprints, slight distortions in the cosmic microwave background. Physicists have looked for such signs, but so far, nothing conclusive has emerged. That hasn't stopped people from trying. Some researchers explore whether certain high-energy phenomena in particle accelerators might hint at extra dimensions, pathways that could connect universes. Others run simulations to see what patterns might emerge if our universe had been brushed by another one in the distant past. A multiverse of multiverses. The rabbit hole goes deeper. Some theorists imagine that different multiverse models could all be true at once. That eternal inflation, many worlds quantum mechanics, and the string landscape might describe different layers of a reality that is itself almost beyond the reach of language. A multiverse made of multiverses, a hierarchy where each level spawns countless more. If that's the case, before the Big Bang stops being a single question with a single answer, it becomes a web of questions. each leading to a wider vista, each vista revealing more than you can hold in your mind. The human response. For you, lying here in the dark, the multiverse can feel like a paradox. On one hand, it makes our universe feel small, less unique. On the other hand, it makes our existence even more extraordinary. Out of all the possible universes, you are in this one, with this physics, in this moment. That's not nothing. That's the result of a cosmic lottery so vast that your very awareness is one of its rarest prizes. It's also humbling. If the multiverse is real, we will never know most of it. The vast majority of reality will forever be beyond our reach, and that's okay. You don't need to touch every wave in the ocean to know the ocean is there. The soft answer. In a way, the multiverse gives the gentlest possible reply to what was there before the Big Bang. It says more universes, an infinite garden with ours being just one bloom. It doesn't need a beginning because it's always in motion. It doesn't need an ending because there's always somewhere else for the story to go. And maybe that's the most sleep-friendly version of the truth, that the universe is not a fragile miracle perched on the edge of nothing, but part of a vast, self-sustaining reality that never needed to start and will never truly stop. So if you ever feel small under the stars, remember, your smallness is part of something so much larger, so much stranger, and so much richer than the word universe can hold. And in that immensity, you are exactly where you're meant to be. Close your eyes and try to picture the Earth. Not the map version with its neat lines and labeled oceans, but the actual sphere, the way it floats in space, curved and seamless. Now imagine standing at the North Pole. If someone asked you to walk farther north, you'd find that the request doesn't make sense. You're already at the farthest north there is. Every step you take leads south. There's no edge, no wall, no secret ice shelf to cross. North simply ends by folding back into the globe itself. Stephen Hawking and James Hartler proposed that the universe might work in a similar way when it comes to time. Their no-boundary proposal takes the idea of the Big Bang and twists it into something far stranger. The possibility that there was no before in any physical sense, because time itself is curved, like the surface of the Earth. In this view, the Big Bang is not a sharp edge where the universe springs out of nothing, but more like the North Pole of time, a place where the direction changes, but the fabric continues smoothly. To see why this matters, think of what we usually imagine when we talk about the start of the universe. We picture a kind of empty stage, and then, bang, everything begins. But that mental picture has a flaw. It assumes the stage was there before the actors arrived. The no-boundary proposal erases the stage. It says the universe didn't start in time. It started with time. Time is part of the set, not something the play was built on. And if time is part of the set, then asking what happened before the Big Bang is like asking what's north of the North Pole. The question collapses under its own weight. The proposal comes out of quantum cosmology, where the universe is treated as a quantum system, a wave function that contains every possible state of reality. In this quantum picture, the very early universe didn't have separate notions of time and space the way we experience them now. Instead, space and time were blended into something called imaginary time, a mathematical dimension that doesn't behave like the ticking seconds we know. In imaginary time, there's no beginning or end, just a smooth geometry that transitions into the real time we inhabit today. It's worth pausing on how radical this is. It doesn't just mean there's no moment before the Big Bang. It means there's no need for one. The entire notion of before is a misapplied human instinct. In the no-boundary model, the Big Bang isn't an explosion into empty space. It's the smoothest possible turning point in the history of the universe. And because there's no edge, there's also no requirement for a cause outside the universe to light the fuse. The question, what caused the Big Bang, becomes meaningless in the same way what's north of the North Pole is meaningless. For many people, this feels unsatisfying at first. We like causes. We like stories that begin with "once upon a time." The no-boundary proposal offers something closer to "it always was" in the only way it could be. But if you sit with it for a while, it begins to feel oddly gentle. There's no cliff where time plunges into nothing. There's just a curve, a horizon, and then a continuation you can't see because the geometry folds it away from you. One of the subtle beauties of the no-boundary idea is that it gives the universe a kind of self-contained elegance. If the universe is finite but unbounded, like the surface of a sphere, then it doesn't need anything outside itself to explain it. There's no outside at all. Everything that exists is part of the same continuous fabric, with no start line and no finish line, only the eternal curve of space-time itself. Critics point out that this is, for now, a mathematical model. It's beautiful on paper, but testing it is tricky. Some suggest that the shape of the universe's early fluctuations, the tiny variations in the cosmic microwave background, might contain hints of whether the no-boundary proposal is true. Others argue that the mathematics of imaginary time is more of a useful metaphor than a literal description of what happened. Hawking himself often moved between the two ways of talking about it, sometimes treating it as an exact picture, other times as a conceptual tool to help us stop asking questions that nature may not be built to answer. And yet, even if it turns out to be only a partial truth, the no-boundary proposal does something important. It breaks our addiction to the idea of a starting gun. It asks us to let go of before as a crutch, and to imagine that the universe doesn't need a foundation in time at all. It invites us to think of reality as something more complete, something that doesn't have to emerge from nothing, because it was never in nothing to begin with. There's a quiet comfort in that. You don't have to picture a void waiting for a spark or an endless regress of earlier universes. You can simply imagine the fabric of reality curving back on itself, graceful and seamless, without sharp edges or abrupt starts. And if that curve feels impossible to visualize, that's all right. The mind is very good at wanting straight lines where none exist. If the no-boundary proposal is right, then the answer to what was there before the Big Bang is simple. There was no before. Time, as we know it, did not yet exist. The universe wasn't born in time, it gave birth to time. And in doing so, it closed the door on the very question that keeps you awake, replacing it with a horizon you can only approach, never cross. If you lean in close enough to anything, the surface begins to lose its smoothness. A polished table turns into a landscape of tiny scratches. A calm ocean reveals ripples, eddies, and the small chaotic dance of droplets. Reality, when you zoom in far enough, resists the idea of being perfectly flat or perfectly still. Physicist John Wheeler imagined that space-time itself, when examined at the smallest possible scale, might behave the same way. He called this seething, ever-changing understructure quantum foam. To seethen. To get there in your mind, you have to dive deep, far deeper than atoms, deeper than protons and neutrons, deeper still than the quarks and gluons that stitch them together. Eventually you reach the Planck scale, a realm so tiny that a single millimeter would be a universe-sized gulf compared to it. At this scale, the very concepts of space and time as continuous fabrics begin to fray. The smooth grid of space-time that Einstein described in general relativity gives way to something restless and turbulent. Tiny fluctuations bubble in and out of existence. The distances and durations we take for granted dissolve into a froth of probabilities. In the quantum foam picture, this turbulence is unavoidable. Quantum mechanics tells us that you can never pin down both the position and momentum of something with absolute certainty. That same uncertainty applies to energy itself. And because energy and the curvature of space-time are linked through general relativity, space-time itself must fluctuate. Over unimaginably short intervals, these fluctuations might be so wild that tiny black holes form and evaporate, wormholes briefly open and close, and entire micro-universes flash into being before vanishing again. It's a strange idea to hold in your mind that beneath the calm stretch of cosmic space is an ocean of chaos, one we never see because it exists on scales far smaller than any particle we've ever touched. But for some physicists, this foam is more than just an oddity. It might be the very birthplace of universes. If the foam naturally spawns fluctuations of all kinds, then perhaps one fluctuation could, under the right conditions, expand instead of collapsing. That expansion could be what we call a Big Bang. In this sense, before the Big Bang could have been nothing more exotic than the quantum foam doing what it always does, bubbling with possibilities, one of which happened to become us. Of course, foam is a metaphor. Space-time at the Planck scale doesn't literally froth like soap bubbles in a sink. The image is meant to capture the unpredictability and constant change, the way shapes and connections might flicker and rearrange faster than any clock could count. Trying to picture it is like trying to imagine the texture of silence. It's not so much an object as a condition, a rule of the game that says reality can never be perfectly still. Some scientists have tried to find evidence of quantum foam by looking at how light travels over vast distances. If space-time were perfectly smooth, then light from distant galaxies would arrive crisp and clear, unaffected by any microscopic jitter. But if the foam exists, it could subtly scatter or blur the light, creating patterns that might be detectable with the right instruments. So far, the results have been mixed. Some observations have placed limits on how foamy space-time can be, but no one has yet caught it in the act. The absence of direct proof doesn't weaken the appeal of the idea, because quantum foam naturally falls out of combining quantum theory with gravity, even in the simplest thought experiments. If space and time are subject to quantum uncertainty, then this restless ground state is inevitable. The real challenge is that we have no way yet of building an experiment small and sensitive enough to touch it directly. The foam remains hidden under the calm surface, like the churning currents beneath a frozen lake. For our question, what was there before the Big Bang? The foam offers a quiet kind of answer. There was no empty stage, no vast void waiting for a cue. There was only a ceaseless shimmer of potential, fluctuations too small for any ruler or clock to mark, each with the chance, however slim, to ignite into something vast. Our universe could be one such ignition. Others might have flared and faded before us. Others might be flaring now beyond our reach. There's something almost intimate about this view. It doesn't place the origin of the universe in some remote, unreachable metaphysical realm, but in the very structure of reality's smallest pieces. The same rules that allow particles to pop in and out of existence in a laboratory vacuum might be the rules that brought all of space and time into being. You are, in a literal sense, built from the same fluctuations that stitched the universe together in its first moments. And if the foam is truly eternal, if it is the base layer of existence, uncreated and indestructible, then before the Big Bang becomes a meaningless notion, the foam simply is, always, without start or finish. In that sense, our universe is not the child of a beginning, but the expression of a process that never needed one. When you lie in the dark and think about this, you might picture the universe floating like a single bubble on the surface of an endless sea. That sea is not still. It swells, ripples, and churns, forever birthing and swallowing possibilities. The bubble you inhabit happens to have grown large enough and stable enough to contain stars and planets and minds. But the sea itself goes on, unconcerned, its surface forever breaking and remaking. If that's the truth, then asking what was there before the Big Bang is like asking what was there before the waves. The answer is, the water was always moving. It always will be. And in that restless movement, there is room for every universe that ever could be. You've probably been told that a vacuum is empty, that it's nothing, a hollow chamber with no particles, no air, no light, just an absence. But in physics, a vacuum is far from nothing. It's a stage where things are happening all the time, unseen, even in perfect emptiness. The laws of quantum mechanics insist that energy can never be exactly zero. There's always a faint hum, a whisper of activity, a baseline restlessness that refuses to go away. This is the quantum vacuum, and it might be the most misleadingly named thing in all of science. In this view, emptiness is not sterile, it's fertile. It is a field in which particles and antiparticles constantly pop into existence, only to annihilate each other almost instantly. These events are called vacuum fluctuations. They happen everywhere all the time, and the only reason you don't notice is that they occur on scales so small and timescales so short that they blur into the background. But what if one of these fluctuations didn't disappear? What if, instead of collapsing back into the quiet of the vacuum, it grew? That's the premise of vacuum fluctuation cosmology. The idea that our entire universe might be the result of such a fluctuation. A tiny patch of the quantum vacuum could have, by some extraordinary statistical accident, created a pocket of space-time that was both dense and energetic enough to trigger expansion. Once expansion began, it could feed on itself, stretching that pocket into something vast. From the outside, it would still be a fluctuation, just one with absurdly lucky initial conditions. From the inside, it would be a universe. It would be us. It's a seductive idea because it replaces nothing with something tangible, something we know exists in a measurable way. Vacuum energy is not speculation. It shows up in experiments, in the Casimir effect, in the way quantum fields behave. The same principles that allow a particle to pop into being for a fraction of a second might, in extreme and rare circumstances, allow for the birth of an entire cosmos. The physics doesn't change, only the scale. But the scale is the sticking point. Quantum fluctuations happen constantly, yet almost all are microscopic and fleeting. For one to give rise to a universe, it would have to break free from the statistical leash that drags nearly all of them back to zero. That's a bit like a wave in the ocean suddenly growing taller than the sky without any storm to feed it. Rare doesn't even begin to describe it. But in an eternal vacuum, one that exists forever, there is time for even the rarest events to happen. And if the vacuum itself has always been there, then perhaps it has birthed an infinite number of universes, each beginning as a fluctuation, each expanding into its own version of reality. This picture has a strange consequence. It makes the Big Bang less of a singular miracle and more of a statistical inevitability. If the rules of quantum mechanics hold everywhere, then the vacuum is always busy, always rolling the dice. And eventually, somewhere, the dice will land in exactly the right way to produce a universe with stable matter, long-lived stars, and life capable of asking where it all came from. Ours just happens to be one where those numbers lined up. Of course, the natural next question is whether there is a deeper reality beneath the vacuum. If our universe came from a quantum fluctuation, what is the vacuum itself embedded in? Is it a property of space-time, or is it something more fundamental, something from which even space-time emerges? This is where physics brushes up against metaphysics. Because the quantum vacuum is not nothing. It's a set of rules, a structure, and structures beg for origins. Some theorists sidestep the problem by suggesting that the laws of physics are eternal, baked into reality without cause. Others speculate that even the vacuum fluctuates between different forms, leading to higher-level meta-fluctuations that could spawn universes with different underlying rules altogether. Vacuum fluctuation cosmology has the added benefit of being conceptually simple in one way. It doesn't require a full reimagining of the laws of nature. It takes what we already know about quantum fields and just lets them play out on the grandest possible stage. But it's also deeply unsettling, because it implies that universes could appear anywhere, anytime, given enough quantum space to work with. And if that's true, it raises the possibility that the multiverse is not an optional extra. It's the default state of existence. It also shifts how we think about beginnings. If the vacuum is eternal, then the Big Bang isn't the first event. It's just one event in a process that has no start. Asking what was there before the Big Bang becomes like asking what was there before the music started, when the truth is that the music has been playing forever. and what you're hearing is just one verse. Lying in the dark, it's easy to get lost in the quiet enormity of this idea. Every particle in your body could be traced back in principle to a ripple in a quantum field, a ripple that might have been part of the largest fluctuation the vacuum has ever produced. And yet that ripple obeyed the same rules as the smallest, shortest-lived blips happening all around you right now. In that sense, you are both ordinary and miraculous, a natural outgrowth of the same restless background that will keep flickering long after our universe fades. If this is the truth, then there was never a moment when nothing existed. The vacuum has always been full, not of matter or light, but of potential. Potential that cannot help but express itself. And sometimes that expression takes the form of a universe. Imagine the universe not as a vast emptiness dotted with stars, but as a vibrating instrument. Every note, every chord, every harmony of existence comes from strings so unimaginably small that if an atom were the size of the observable universe, a string would still be smaller than a tree in your front yard. String theory proposes that these tiny filaments are the true foundation of reality. Everything, electrons, quarks, even gravity itself, is just the vibration of these strings at different frequencies. You are, in the most literal sense possible, a symphony of vibrations. If that's true, then the Big Bang might not be the beginning at all. In the version of events inspired by string theory, there could have been a time before the Big Bang when the universe existed in a very different state. One dominated not by point-like particles, but by these fundamental strings and higher dimensional objects called brains. Space and time as we know them might have been tangled, folded, and compact in ways that don't exist today. The hot, rapidly expanding universe we live in could have been born from the transformation of that earlier state, like a new movement in an endless piece of music. One of the most striking ideas is that our universe might be a three-dimensional brain floating in a higher dimensional space. This space is sometimes called the bulk, and it could contain other brains, parallel universes, drifting like sheets in an invisible wind. In some scenarios, these brains can collide. A collision between two brains would release an enormous amount of energy, potentially enough to create all the matter and radiation in a universe. From our point of view inside one of the brains, this event would look like a Big Bang, but in reality, it would just be the aftermath of a higher dimensional crash. This concept is sometimes called the ekpyrotic model, from a Greek word meaning conflagration. It's an attempt to explain the Big Bang not as the creation of everything from nothing, but as the result of a pre-existing process in a larger, unseen reality. And if such collisions happen, they might not be rare. In some versions of the theory, brains move in cycles, approaching, colliding, separating, and drifting back together over vast spans of time. Each collision would set off a new Big Bang in the brains involved. In that sense, our universe could be just one of many, born from a rhythm that has been playing out far longer than our own timeline. The beauty of this picture is that it provides a concrete before without requiring a singularity. Instead of time and space starting from an infinitely small point, they could have existed in a different form all along, reshaped by the collision. The temperature, density, and structure of our early universe would then be the result of how the brains struck each other, at what angle, with what speed, and in what state. These details could even leave subtle traces in the large-scale structure of the cosmos, or in the cosmic microwave background, patterns that scientists are still trying to detect. But there's an even deeper twist. String theory also suggests that time itself might behave differently at extremely small scales. Some models propose a duality, in which the laws of physics remain the same whether the universe is expanding or contracting, meaning that a contracting phase before the Big Bang could mirror the expanding phase we're in now. In this view, the Big Bang wasn't a beginning, but a bounce, a moment when contraction reversed into expansion. And in the realm of strings, that bounce could be smooth, without the infinities that plague traditional cosmology. The mathematics of these scenarios is intricate. involving extraspatial dimensions curled up so tightly we could never see them directly. These dimensions could shape the properties of our universe in profound ways, determining the masses of particles, the strengths of forces, and even the nature of dark energy. If you think of the universe as a piece of music, these hidden dimensions would be the resonant chamber that gives the notes their tone. Change the shape of that chamber, and the entire melody changes. For our question, what was there before the Big Bang? String theory's pre-Big Bang ideas offer a vision that's rich and strange. There was no empty void, no pure nothingness. There was a higher dimensional stage where brains drifted, collided and reformed, where strings vibrated in patterns we can't yet hear, where time may have flowed in a loop or folded back on itself. The before was just as real as the after, but governed by a physics so alien to our current world that it's almost impossible to imagine. And yet, in a way, that's the point. Our familiar universe, with its atoms, stars, and galaxies, might be just one phase in a much larger structure of reality. The Big Bang becomes not a one-time miracle, but one note in a cosmic song that has been playing forever, perhaps in harmonies we will never hear. You are a listener inside a single verse, and the rest of the composition extends beyond any horizon you could ever reach. Whether or not these ideas turn out to be true, they challenge the deepest assumption most people have about the universe, that there must have been an absolute start. String theory whispers that maybe there wasn't. Maybe the music never began. Maybe it's simply always been there, vibrating through the unseen dimensions, waiting for each of us to notice the small part of it we can hear before we fade back into the silence. Imagine walking in a forest where the trees are so tall and the air so still that you lose all sense of direction. You notice a path beneath your feet, soft with fallen leaves, and after hours of wandering you realize that the path is leading you back to where you began. But nothing looks exactly the same. There are new leaves on the ground, the light is different, and yet there's a feeling that you've been here before. Time in this forest isn't a straight line. It loops, but in each loop the details shift. This is something like what Roger Penrose envisioned with his conformal cyclic cosmology model, or CCC for short. It's an idea so strange that even among cosmologists it stands apart. Penrose's starting point is simple but radical. Perhaps the universe's distant future and its distant past are connected in a way that makes them almost the same. The end of one universe could flow seamlessly into the beginning of the next, not as a rebound or a violent crunch, but as a kind of elegant handover, one aeon giving birth to another. To see why he thought this was possible, you have to imagine what happens to the universe in the far, far future. Galaxies drift farther apart, stars burn out, one by one. Black holes devour whatever's left, and over unthinkable spans of time even those black holes evaporate through Hawking radiation, leaving only the faint whisper of particles scattered in an ever-expanding space. In this future, the universe contains almost nothing except light, massless particles that care nothing for size or scale. In such a universe there is no clock to measure time, because all the events that could mark it have faded away. This is where Penrose's key insight comes in. If a universe reaches a state where everything is massless, then the actual scale of the universe no longer matters. A photon doesn't know whether the space it's crossing is 1 billion kilometers or 1 billion trillion kilometers. It just moves. In the mathematics of space-time, you can then stretch or shrink the empty, light-filled universe without changing any of its essential physics. This ability to ignore scale is what's meant by conformal in conformal cyclic cosmology. Penrose's bold leap was to say, if you can shrink that final, cold, empty universe down to a kind of mathematical point, there's nothing to stop you from treating it as the beginning of a new Big Bang. The end of one aeon becomes the start of the next. No violent bounce, no catastrophic singularity, just a smooth, scale-free transition from one era of reality to another. And this process could have been happening forever. Our universe in this view is just one in an infinite sequence of aeons, each born from the faded-out light of the one before it. What makes CCC so unusual is that it's not about smashing the universe back together, as in some cyclic models, nor about spawning bubbles in eternal inflation. It's about redefining what it means for time to pass and for scale to matter. In the final stages of an aeon, when everything is massless, there is no difference between very large and very small that allows the equations of general relativity to link the infinite future of one universe to the hot, dense beginning of the next, without any contradiction. Penrose has even suggested that we might see evidence of past eons in our own sky. According to CCC, certain massive events in a previous universe, such as collisions between supermassive black holes, could leave faint imprints that survive the transition between eons. These would show up as subtle patterns in the cosmic microwave background, perhaps as concentric circles of unusually uniform temperature. Penrose and some collaborators have claimed to see hints of these circles in data from satellites like WMRP and Planck, though the interpretation is hotly debated. Many cosmologists remain unconvinced, arguing that the circles could easily arise from random noise. Whether or not those hints are real, the philosophical implications of CCC are staggering. In this picture, before the Big Bang isn't a mysterious void or a realm of strange physics. It's simply another universe, unimaginably old, that had reached its graceful end. The matter and energy of that aeon have been erased by time's long hand, leaving only the pure geometry of space-time, ready to be reshaped into something new. Our Big Bang then was just the next note in a melody that has no first note at all. There's a kind of quiet poetry in this vision. If CCC is correct, then everything that exists now is both the product of a past universe and the seed of a future one. Your atoms were once part of a cosmos so ancient that no remnant of its structure remains. And someday the particles that make you will drift into a state where distance no longer matters, where scale dissolves, and where a new universe is born. You will have been part of both the ending and the beginning, even if no trace of you remains in either. It's not the most intuitive way to think about time, because we live in a world where scales matter. A kilometer is not the same as a centimeter. An hour is not the same as a year. But CCC asks you to imagine a realm where such distinctions vanish, where all that's left is the shape of space-time itself, stripped of its clocks and rulers. In that realm, endings and beginnings are the same thing, and the universe is a chain of them, stretching without limit in both directions. If you've ever walked a circular path and found yourself back at the starting point, you know the strange mix of familiarity and difference it can hold. CCC is like that, but on a scale where each loop contains the birth and death of an entire cosmos. And if it's true, then when you ask what was there before the Big Bang, the answer is simple. There was another universe, and before that, another, and before that, another, as far back as the mind, and perhaps even reality itself can reach. Try to imagine space not as the three-dimensional emptiness you walk through, but as the surface of something larger. We're used to thinking of our universe as everything, an infinite or at least unbounded arena containing all that is. But in certain versions of string theory and M theory, our universe is just one three-dimensional slice of a reality, with more dimensions than we can see. This slice is called a brane, short for membrane, and it's not floating in nothing. It exists within a higher dimensional expanse called the bulk. In this picture, the bulk is like a vast invisible ocean, and the branes are like enormous flat rafts drifting through it. We live entirely on one of these rafts, unable to see or step off it, because all the particles and forces we know, light, matter, electromagnetism, are tied to the brane itself. Only gravity can seep between branes, which is why we might not feel or see their presence. The idea sounds fantastical, but it comes straight out of attempts to unify the laws of physics, where extra dimensions aren't optional, they're part of the underlying math. Now imagine that there is another brane, parallel to ours, hidden from us in one of these extra dimensions. It could be almost identical to our universe, or utterly alien. It might be drifting slowly toward us, pulled by forces in the bulk that we can't measure. And then, after billions or trillions of years, it could collide with ours. That collision is the heart of the brain collision hypothesis for the origin of our universe. In this model, the Big Bang wasn't an explosion from a single point, but the aftermath of two enormous brains slamming into each other. The energy of the collision would heat both brains, flooding them with matter and radiation, kickstarting expansion. Inhabitants of either brain, if there were any, would experience the collision not as an impact from outside, but as the sudden appearance of a hot, dense universe erupting into existence. For us, it would have been indistinguishable from the Big Bang itself. This scenario offers a tantalizing answer to what was there before. The answer is another brain, and perhaps even another universe, existing alongside ours in the bulk, following its own history until our paths crossed. And before that, the brains could have been moving apart from a previous collision, part of a repeating cycle of approach, impact, and separation. In that case, the Big Bang wasn't the first time our brain had been lit with matter and energy. It was just the most recent ignition in a story that stretches into the deep past. The physics here is slippery, because the bulk itself, this higher dimensional space, isn't bound by the same rules we see inside our brain. Dimensions beyond the familiar three could be infinite in size, or they could be curled up tightly at scales smaller than an atom. The forces that move brains through the bulk could be gentle drifts or irresistible pulls. In some models, brains can even ripple like fabric, sending out waves into the bulk that might subtly affect others long before they collide. If this idea sounds like science fiction, it's worth remembering that it comes from serious attempts to answer stubborn questions in cosmology. For example, why is our universe's expansion so smooth on large scales? Why do the laws of physics seem so finely tuned for the existence of matter and life? Brain collisions offer an explanation. The smoothness comes from the uniform energy of the collision, and the tuning comes from the specific way brains can interact in the bulk. One of the more intriguing aspects of the hypothesis is that it could, in principle, leave fingerprints. If the collision between brains wasn't perfectly uniform, if one part of the brain hit slightly earlier or with more force than another, those differences might leave subtle patterns in the cosmic microwave background. Detecting such patterns is difficult, and so far no definitive evidence has been found. But the idea remains on the table, especially for cosmologists who see the Big Bang as too neat to be the very first moment of everything. From a philosophical perspective, the brain collision hypothesis is both humbling and thrilling. Humbling because it suggests that our universe is not all there is. It's just one sheet among many in a vast stack. Thrilling because it means there's a deeper stage on which the drama of universes unfolds, a stage we might never step onto, but which shapes our fate nonetheless. If the hypothesis is correct, then before the Big Bang was not an empty void, but an entire three-dimensional cosmos, as rich and real as our own, separated from us only by a sliver of higher dimensional space. It also raises strange possibilities about the present. If there are other brains drifting in the bulk, collisions are not one-time events. Somewhere out there, two other brains could be on a collision course right now, setting the stage for another Big Bang in a reality we will never know. And perhaps in the far future, our own brain could meet another again, igniting a new aeon of stars and galaxies, starting the story all over. Thinking about this in the quiet of night, you might picture two immense, invisible worlds gliding toward each other, their surfaces stretched flat across horizons you can't see. No sound, no wind, no warning, just the slow, inevitable movement through the hidden dimensions. Then in an instant they meet, and the energy of that meeting blossoms into light, matter, and time itself. Somewhere in that new blaze, minds like ours begin to wonder how it all began. If that's true, then the question, what was there before the Big Bang, becomes both simpler and stranger. Before there was another universe, not a ghostly nothing, not a realm of pure mathematics, but a living, evolving cosmos, riding on its own brain, waiting for the moment when its path would cross ours and give birth to everything we know. Picture space not as an infinite smooth sheet, but as a weave, a fabric made from tiny discrete threads. To the human eye, a woven cloth looks continuous, but if you hold it close enough, you see the tiny stitches. Loop quantum gravity takes this idea seriously for the universe itself. It says that space-time is not infinitely divisible. There is a smallest possible scale, a fundamental grain to reality, and it is woven together by quantum loops. No matter how hard you try to zoom in, you cannot cut space into smaller pieces than these loops. They are the building blocks of the cosmos, the indivisible threads from which all distances, times, and shapes are made. In the version of this theory applied to the entire cosmos, loop quantum cosmology, this woven texture changes how we think about the beginning of the universe. In standard general relativity, if you roll the clock back far enough, all matter and energy in the universe gets crushed into a single point of infinite density. That's the singularity, and it's where the math breaks. But in loop quantum cosmology, the weave of space-time has a built-in resistance to such extremes. As the universe contracts and densities rise, the quantum geometry creates a kind of repulsive force, so faint that we never notice it under normal conditions, but overwhelming when everything is squeezed toward the Planck scale. That repulsion is the key to avoiding the singularity. Instead of collapsing into an impossible point, the universe reaches a smallest possible size, a minimum volume dictated by the quantum loops, and at that moment the pressure reverses. The contraction stops. The universe bounces. The Big Bang in this view is not the birth of everything from nothing. It's the rebound from a previous cosmic phase, one where the universe had been shrinking for billions or trillions of years. If this is true, then before the Big Bang was another universe much like ours, but moving in reverse. Galaxies were drifting closer, cosmic structures collapsing into a tighter and tighter space. Eventually, everything was packed into a state so dense that quantum gravity took over, flipping the direction of time's arrow and beginning the expansion we now live in. Our universe could be just one swing in an endless pendulum, each swing a full cosmic cycle. This vision changes the emotional texture of cosmology. In the standard picture, the Big Bang is an absolute beginning, an instant that divides existence into before nothing and after everything. In loop quantum cosmology, there is no such division. Time extends in both directions, and the Big Bang is just a turning point, like the moment when a ball thrown into the air stops rising and begins to fall. There's no ultimate creation, only an eternal interplay between contraction and expansion. It's a model that also fits neatly with certain philosophical instincts. Many people are uneasy with the idea of absolute beginnings. They wonder what lit the fuse, what caused the first moment. The Big Bounce sidesteps that entirely. There is no first moment to cause. The universe simply is, forever oscillating between large and small, never reaching either infinity or zero. Testing this idea is difficult, but not hopeless. If a previous universe really existed before our own expansion, it might have left traces in the form of patterns in the cosmic microwave background, subtle anomalies that standard inflationary theory wouldn't predict. Some researchers have even claimed to find hints of such patterns, though the evidence remains contentious. There's also the possibility that certain features of gravitational waves, the ripples in space-time caused by massive cosmic events, could carry echoes of a pre-bounce universe. But perhaps the most powerful part of this idea isn't its testability, it's the way it reframes our place in the cosmos. If loop quantum cosmology is correct, then everything you see, every star, every planet, every atom was once part of another universe, and everything here will someday contract again, drawn back toward that moment of reversal, only to emerge on the other side in a new expansion. The universe is not a line with a beginning and end, but a breathing thing, inhaling and exhaling forever. You might wonder if the universe that came before ours looked anything like this one. Could it have had galaxies, stars, life, or were its constants and structures different enough to make it unrecognizable? The mathematics of the bounce doesn't demand that each cycle be identical. It only demands that expansion follows contraction. That means every bounce could be a fresh arrangement, with its own physics, its own stories, its own chance for beings like us, or entirely unlike us, to wonder about their origins. And in that wondering lies a quiet continuity. Every cycle might forget the details of the one before it, but the pattern itself remains, encoded in the fabric of space-time. We are part of that pattern, just as whatever came before was, and whatever comes after will be. The loops that make up the weave of the cosmos don't remember you, but they remember the rules that allow you to exist. Lying here in the dark, it's almost soothing to think of the Big Bang not as a one-time miracle, but as a natural part of a rhythm that has been going on forever. The stars above you are the latest verse in a song that never began and will never end. The silence before you were born, and the silence after you're gone are both part of the same breath. And the breath belongs to something far older than any universe we could see. If this is true, then before the Big Bang was not nothing, it was everything, moving in the opposite direction, rushing toward a moment that would turn it inside out. And one day, unimaginably far from now, the expansion we live in will slow, the galaxies will gather, and the universe will inhale again, drawing all of us back toward the weave, ready for the next bounce. If you've ever looked at a hologram on a credit card or a souvenir postcard, you know the trick. The image looks three-dimensional, as though you could reach inside it, yet the surface holding it is perfectly flat. Move your head, and the image seems to shift, revealing details from new angles. The magic is that all the information about the three-dimensional picture is encoded on a two-dimensional surface. In the 1990s, some physicists began to wonder if the entire universe might work the same way. What if everything we see, every star and planet, every moment of our lives, is a kind of cosmic hologram, three-dimensional reality projected from a two-dimensional boundary? This idea, known as the holographic principle, isn't just a poetic metaphor. It came from hard physics. From a puzzle about black holes, in the 1970s, Jacob Bekenstein and Stephen Hawking discovered something strange. The amount of information you can store inside a black hole, the number of possible internal states it can have, is proportional not to its volume, but to the surface area of its event horizon. That's like saying the capacity of a library depends not on how many shelves it has, but on the size of its front door. This finding suggested that the deepest description of reality might live not in the space we move through, but on a surface that encloses it. If that's true for black holes, some physicists wondered why not for the whole universe? Perhaps all the information that makes up our universe is encoded on a distant two-dimensional surface, like the edge of space-time itself, and what we experience as three dimensions is just a projection of that data. From our perspective inside the projection, everything feels solid and three-dimensional, just as the figures in a hologram look real even though they're flat. Now, imagine applying this to the Big Bang. In the standard view, the early universe was a hot, dense soup of particles expanding and cooling over time. In the holographic view, the Big Bang might have been the moment when the projection began, a transition in the underlying two-dimensional description that unfolded into the three-dimensional reality we inhabit. Before the Big Bang in this picture might exist entirely in that two-dimensional framework, a place without the familiar concept of volume at all. It's an unsettling shift. We are so used to thinking of reality as out there, extending in depth, that the idea of it being a kind of encoded illusion feels almost like a philosophical prank. But the holographic principle is supported by serious work in string theory, particularly through something called the ad-ease CFT correspondence, which shows mathematically that certain gravitational systems in higher dimensional space can be exactly equivalent to quantum systems in fewer dimensions. Gravity on the inside can be completely described by quantum mechanics on the boundary. For our question, what was there before the Big Bang? The holographic idea offers a unique answer. The before might not be another physical space-time at all, but a static, two-dimensional structure carrying the seeds of our universe in its patterns of information. The Big Bang could be seen as the unfolding of that information into the space and time we know. In that case, there's no need for a singularity, no need for infinite densities or temperatures, just a shift from one kind of description to another. This isn't to say that our world is fake in the way of a computer simulation. A hologram isn't fake, it's just a different way of storing and displaying information. The physical laws we observe, the matter we touch, the light we see, are all real within the projection. What changes is our understanding of where those laws come from. Instead of being fundamental properties of a 3D world, they might be emergent, arising from deeper laws written on the universe's boundary. One of the most intriguing consequences of the holographic principle is that it could reconcile some of the tension between quantum mechanics and gravity. In our usual picture, these two pillars of physics clash at extreme scales, like the moment of the Big Bang. But if the Big Bang was not a 3D singularity, but the start of a holographic projection, the conflict might dissolve. The physics of the boundary could be fully quantum, sidestepping the breakdowns that plague the standard model of cosmology at its earliest moments. It's worth admitting that this is still a highly theoretical idea. Evidence for the holographic principle in cosmology is subtle and indirect. Some studies have tried to see if the patterns of the cosmic microwave background, the afterglow of the Big Bang, contain signs of a lower dimensional origin. There have been tantalizing hints, statistical anomalies that could fit the holographic picture, but nothing that yet rises to the level of proof. Still, the principle is so powerful in other areas of physics that many researchers take it seriously as a guide to understanding the universe's beginning. Thinking about this in the quiet of night, you might imagine the whole of reality as a grand image shimmering on an invisible film, projected inward to create the illusion of depth. We are figures in that image, made of the same encoded light as the stars and galaxies. If that's true, then before the Big Bang might be like the film before the light hits it, containing all the patterns, all the data, but not yet unfolded into the living motion of space and time. This changes how you think about origins. In a sense, the Big Bang wouldn't be the start of existence. It would be the start of the projection. The true origin might be in the timeless arrangement of information on the boundary, a structure that could have existed forever, or arisen from laws we have not yet glimpsed. The before could be a static perfection, a kind of cosmic blueprint waiting for the moment when the hologram lights up and becomes a universe. If the holographic universe is real, then our search for the beginning might one day lead not outward, but to the edge, the place where all our three-dimensional reality reduces to a simpler, stranger, two-dimensional truth. And perhaps, just perhaps, that truth has been there all along, holding every possible history, every possible future, in the silence before time began to move. We grow up with the idea that space and time are the stage on which the drama of the universe plays out. They feel permanent, unshakable, the canvas beneath every brushstroke. Even when we talk about the Big Bang, we often imagine it as happening in space, at a time as though those two things were already waiting, like a blank sheet of paper waiting for the first words to be written. But what if the paper itself didn't exist at first? What if space and time were not the starting conditions, but the first things to appear? This is the unsettling suggestion behind the idea of emergent space-time, that the fabric of reality is not fundamental, but a kind of construct, something that forms out of deeper, more basic ingredients that don't themselves live in space or time. It's a bit like realizing that the ocean isn't a basic feature of the world, but the collective result of countless molecules of water, moving and interacting according to rules that make the larger surface waves possible. In the emergent space-time view, the waves are what we call space and time, and the water molecules are something we haven't yet fully identified. In this picture, the question, what was there before the Big Bang, may not make sense in the way we think it does. Before is a time word, and if time itself didn't exist yet, then we are trying to use a tool that wasn't even part of reality at that stage. It's like trying to measure the temperature of a dream. It assumes a property that isn't relevant to what's actually there. The Big Bang could have been less of a creation event and more of a phase transition, a shift from a timeless, spaceless state into one where space and time began to emerge as usable concepts. Physicists exploring this idea often look for clues in quantum mechanics and in the strange relationships between entanglement and geometry. One particularly suggestive approach is the realization that certain patterns of quantum entanglement, the way particles share information instantaneously across distance, can be directly mapped to the geometry of space-time itself. In other words, the fabric of space might be the network of these entanglements, woven together by the way quantum states are connected. If that's true, then before space-time existed, there might have been only this abstract web of relationships. No distances, no durations, just pure information and correlation. In some models, this pre-space-time reality is described in purely mathematical terms, a set of rules for how things interact, without any reference to where or when they are. Space and time emerge when enough of these interactions occur in the right patterns, producing the illusion of a continuous three-dimensional world evolving through moments. In this sense, time is not a river we drift along. It's a collective effect, like the way heat emerges from countless particles in motion. Without those motions, there is no heat. Without the right kind of interactions, there is no time. If this is true, the Big Bang becomes the moment when the deeper rules of the universe shifted into a regime that allowed space and time to crystallize out of the chaos. The before might have been timeless, but not empty, full of raw potential, seething with the relationships that would soon give rise to locations, durations, and the possibility of change. The birth of the universe was the birth of the very stage we now stand on, and before that stage existed, our most basic intuitions about reality simply didn't apply. This view also changes how we think about causality. In our world, causes precede effects, because time gives them an order. But if time itself emerged, then there might have been a kind of proto-causality before it. Rules of transformation that didn't involve sequences in the way we understand them. Something could give rise to the universe without happening earlier, because earlier wasn't yet a meaningful concept. For our human minds, steeped in clocks and calendars, this is a deeply alien way of thinking. But for the physics, it might be the only way forward. There are hints that this isn't just philosophical speculation. Some researchers are trying to derive the equations of general relativity, the theory of gravity and space-time, from purely quantum systems that don't start with space built in. In certain models, space-time pops out naturally from the collective behavior of the underlying quantum elements, much the way the smooth surface of water emerges from countless jostling molecules. If these ideas can be sharpened and confirmed, they would mean that space-time isn't the foundation of physics, it's a structure built on something even deeper. And what of before the Big Bang in this framework? You could think of it as the unassembled pieces of reality, existing without the framework we live in. If space and time are like the playing field, then before was when the field hadn't been marked or flattened yet, when the pieces of the game existed, but without positions, without moves, without a clock to track the play. The Big Bang was the instant the field took shape and the clock began ticking, but the players, the fundamental entities or rules beneath it all, may have been there all along, just not yet arranged into a world that looks anything like ours. From this angle, the birth of time is not the most mysterious thing, it's the most natural. Time is what you get when the underlying reality organizes itself in such a way that one state leads to another in a consistent fashion. Before that, change might have existed in some abstract sense, but not in the way we experience it. And when the right conditions arose, change acquired a direction, a sequence, and we call that sequence time. Thinking about this as you drift towards sleep, you might picture the universe not as something that exploded into being, but as something that condensed, like a fog coalescing into drops of water. The fog was the pre-space-time state, hazy and formless, full of connections but with no distances between them. The drops are the space-time we inhabit, each one a coherent patch where reality has structure, where you can point to here and there, then and now. The Big Bang was the first drop to form, the one we're still floating inside. And if this is right, then asking what was there before the Big Bang is a little like asking what shape a cloud had before it formed. It wasn't a shape yet. The before was a realm without places or moments, and we are the children of the first moment when places and moments became possible. Close your eyes and imagine the universe not as a place but as a possibility, not as a vast expanse dotted with stars and galaxies, but as something that exists everywhere and nowhere at once, a shimmering cloud of potential outcomes, each one waiting to be chosen. This is the picture that emerges when you think of the universe itself as a quantum wave function. It's not just the particles inside the universe that obey quantum rules, it's the entire cosmos that might be described by one grand, all-encompassing wave of probability. In ordinary quantum mechanics, the wave function is the mathematical object that holds every possible state of a system. For a single electron, that might mean all the places it could be, all the momenta it could have. For a photon, it might mean every possible polarization. The wave function evolves smoothly, governed by the Schrödinger equation, until something happens that forces it to take on one specific outcome, a process we call measurement or collapse. Before that moment, the particle is not in one state. It's in all of them at once, a superposition of possibilities. Now, take that same logic and apply it to everything. The stars, the empty space between them, the entire sweep of cosmic history. The system in question is the universe itself, and its wave function contains every possible version of that universe. Different amounts of matter, different laws of physics, different histories, all encoded in a single mathematical object. Before the Big Bang became the hot, expanding universe we observe, the universe's wave function might have existed in a state where all those versions were equally real in potential, but none yet realized. This is where the question, what was there before the Big Bang, gets reframed in a way that's both mind-bending and strangely peaceful. In the wave function view, the before could have been a pure superposition. No definite geometry, no fixed size, no concrete moment of time. It wasn't that nothing existed, it's that everything possible existed simultaneously, in a state that defies our everyday categories. The Big Bang would then be the moment when that superposition resolved into one specific branch of reality, the one we live in. Physicists like James Hartle and Stephen Hawking have explored this through the wave function of the universe approach, where instead of treating the cosmos as an object inside time, they treat it as something whose quantum description includes time as one of the outcomes. In this framework, time itself is part of what the wave function can contain, meaning there is no sense in which time flows before the Big Bang. It simply isn't defined yet. The moment of the Big Bang is less like an explosion and more like the selection of one particular history from an infinite library of possible histories. The strange thing about quantum mechanics is that it doesn't require an observer in the traditional sense. The universe's wave function can collapse into a definite form through processes that have nothing to do with human measurement. Interactions between different parts of the system, or the decoherence that happens when quantum possibilities become entangled with countless degrees of freedom. In the early universe, that could mean that as soon as certain physical conditions were met, the vast web of possibilities began to thin down into the specific structure we now see in the sky. If this is true, then the before the Big Bang was not empty, but so full of potential that it had no need for space or time to contain it. Every possible geometry, every possible energy distribution, every possible timeline was there, folded into a single undivided whole, and the Big Bang was the unfolding, the moment when the universe chose or was forced into one particular melody from the endless chord. Of course, the universe's wave function is not something we can measure directly. We can only infer it from the patterns we see in the cosmic microwave background, from the distribution of galaxies, from the delicate balance of the fundamental constants. If those patterns match what we'd expect from a universe that began as a superposition of possibilities, then the wave function picture gains strength. And indeed, Some inflationary models and quantum cosmology calculations suggest that the initial conditions of the universe are better understood as a spread of possibilities rather than a single sharply defined state. This perspective also opens the door to the idea of the multiverse, not as a separate speculative concept, but as a natural consequence of quantum mechanics. If the universe's wave function contains many possible versions of reality, then in some interpretations, such as the many worlds interpretation, all of those versions are real, branching away from each other as the quantum possibilities decohere. Our Big Bang would then be just one branch, one collapse, one unfolding among countless others. Thinking about this in the stillness of night, you might imagine the universe before its birth as a vast ocean with no surface. Every ripple in that ocean is a possible cosmos. The Big Bang was the moment one of those ripples rose high enough to break into a wave, spilling forward into the world we now inhabit. The rest of the ocean is still there, full of other ripples that will never touch our shore. It's a humbling view, because it suggests that our universe is not special in the way we might like to think. It's just one realized possibility among infinitely many unrealized ones. But it's also strangely comforting, because it means the Big Bang didn't happen in isolation. It happened as part of a much larger tapestry of possibility, a tapestry so vast that it doesn't need beginnings or endings to make sense. And if you carry that thought further, it means that before the Big Bang wasn't a time at all, but a condition, a timeless, spaceless fullness in which all futures existed equally. The moment of the Big Bang was the moment when one future became the present. And now, billions of years later, you are a small but integral part of that present, a single note in the melody the universe chose to play. Imagine you have a ball resting in a shallow dimple on a hillside. From where it sits, the ball seems stable. It's not rolling, it's not moving, and to an observer it might look like it's in its natural resting place. But if you could zoom out and see the whole hill, you'd notice something important. The ball isn't at the very bottom. There's a deeper valley just beyond a small ridge. Right now it's stuck in a false resting place, a false equilibrium. With the tiniest push, it could roll over the ridge and fall into a state that's even more stable than the one it's in now. That moment of rolling over, that abrupt, irreversible change, is what physicists call a phase transition. In the language of quantum field theory, a false vacuum is like that shallow dimple. It's a state that appears stable, but isn't truly the lowest energy configuration of the vacuum. The vacuum isn't nothing in physics. It's the energy state of empty space itself, shaped by the fields that permeate the universe. In a false vacuum, the universe's fields are arranged in a way that keeps them stuck in a higher energy state, even though a lower energy, more stable configuration is possible. It's as though the entire cosmos is balanced in a delicate position, waiting for the smallest fluctuation to nudge it into a transformation. Now picture the very early universe existing in such a false vacuum state. It's stable enough to persist, but it's carrying excess energy. Then, at some point, through a quantum fluctuation, or through the accumulation of tiny instabilities, that false vacuum decays. When it does, the excess energy locked into it is released in an instant, and space itself undergoes a radical transformation. In one form of the theory, this release of energy is what ignited the hot, expanding universe we know as the aftermath of the Big Bang. This is where the idea of a cosmic phase transition comes in. You've seen phase transitions before, water freezing into ice or boiling into steam. At the molecular level, these transformations involve the rearrangement of particles into a different state. In a cosmic phase transition, it's not water molecules changing. It's the fundamental fields of physics reconfiguring themselves. The before might have been a cold, dark, featureless false vacuum. The after was a sea of high-energy particles and radiation, rushing outward in a burst of expansion. The false vacuum idea dovetails neatly with inflationary cosmology. In many inflation models, the universe begins in a false vacuum whose energy drives the rapid, exponential expansion of space. During this period, the universe is smoothed out, flattened, and stretched far beyond its initial size. When the false vacuum finally decays into the true vacuum, inflation ends, and the released energy reheats the universe, filling it with the matter and radiation that eventually form stars, galaxies, and everything we see today. One of the remarkable things about this picture is how it reframes the Big Bang. Instead of being the ultimate beginning, the Big Bang becomes the afterglow of a transition, the moment when space changed its very nature. Before wasn't nothing. It was a field filled with latent energy, poised on the brink of transformation, and that brink could have been balanced for an immeasurable length of time. In some models, the false vacuum could be eternal, with patches of it decaying into true vacuum in scattered places, each decay spawning a new expanding universe. That would make our cosmos just one bubble in an endless froth born from the same underlying field. If this all sounds precarious, it is. In principle, even now, our universe could be in a false vacuum state, just not the lowest possible one. If so, then it's possible, though unlikely on human timescales, that a tiny fluctuation could trigger vacuum decay again. The transition would send a bubble of true vacuum expanding outward at nearly the speed of light, rewriting the laws of physics in its wake. Anything it touched would be annihilated instantly, not through heat or violence, but by the sheer incompatibility of the new vacuum's rules with the matter and forces of the old one. This isn't meant to be a bedtime story, but the thought is an oddly perfect reminder of how fragile and provisional our universe might be. From a philosophical standpoint, the false vacuum model is fascinating because it provides a concrete physical mechanism for the Big Bang without requiring that time itself had a beginning. If the false vacuum existed indefinitely, then the decay that led to our universe could be just one of infinitely many such events scattered across the timeless expanse of the larger vacuum. The Big Bang would be the local beginning of our space-time, not the absolute start of reality. Thinking about this in the stillness of night, you might imagine the pre-Big Bang universe as a vast, empty plane, perfectly flat, perfectly still, stretching forever in all directions. Nothing happens there for ages, not because nothing can, but because the landscape is stable enough to last. And then, in some corner, a tiny fluctuation pushes a patch of this plane into a lower valley. The change cascades outward at unimaginable speed, reshaping the plane into hills and valleys, seeding light and matter, setting the stage for all the complexity to come. That expanding patch is our universe, and the rest of the plane is still out there, waiting, unchanged. If that's the truth, then before the Big Bang was a state not of chaos but of perfect silent balance. The drama began only when that balance tipped, and space itself fell into a new form. The echo of that fall is all around us, in the microwave afterglow of the Big Bang, in the galaxies that still rush away from each other, in the fact that we are here at all, thinking about the ridge that our universe once rolled over. We are used to stories with beginnings, birthdays, opening chapters, the first crack of dawn after a long night. Our minds cling to the notion that everything starts somewhere. Even the word universe carries that hidden assumption, as though it must have sprung into being at a particular moment, after which everything else unfolded. But there is another way to look at it, a way that removes the idea of a first moment entirely, the eternal universe hypothesis. In this view, the cosmos has always existed in some form. It has no birthday, no first breath, no edge you can stand at and point back toward nothing. To grasp this, you have to let go of the image of time as a line with a dot at one end and an arrow stretching forward. Instead, imagine time as an unbroken ribbon that extends forever in both directions. If you start walking along it, you never reach the start because there isn't one. Every moment has a moment before it, and every moment after it is just another link in the chain. The Big Bang in this picture wasn't the creation of the universe. It was simply one chapter in an endless book. One way to frame this is to say that the Big Bang was a change of state, not a beginning. The universe could have existed in a very different form beforehand, colder, hotter, smaller, larger, perhaps unrecognizable compared to what we see now. That earlier state might have been static for an immense span of time, Or it might have been evolving in ways our current physics can't yet describe. Then, for reasons that could be physical, statistical, or even inevitable, the universe shifted into the hot, dense phase we call the Big Bang. Expansion began, structures formed, stars were born, but all of that was built on top of something older. If this is true, then the phrase "before the Big Bang" is just shorthand for "in the previous era of the eternal cosmos." That era might be impossible to see directly, because any traces it left were erased or scrambled by the violence of the Big Bang, but it could still influence our reality indirectly, in the values of the constants of nature, in the overall shape of the universe, or in subtle patterns in the oldest light we can detect. The eternal universe hypothesis doesn't require magic or a miraculous creation event. It just extends the logic of continuity backward without limit. Of course, infinity is hard for us to hold in our heads. We can say the words, but the mind keeps trying to picture an edge, a starting point, a moment of once there was nothing, and then removing that moment can feel like cutting away the ground under your feet. If the universe has always existed, then there was never a time when it began, and never a time when it will end. It's not a circle in the sense of repeating exactly. It's an unending fabric, weaving itself without pause. From a physical standpoint, there are several ways an eternal universe might work. In some models, the cosmos is infinitely old and unchanging on the largest scales, even as regions within it evolve, collide, and transform. In others, it undergoes an endless sequence of transitions, expansions, contractions, reorganizations, without ever hitting an absolute reset. In still others, the universe is part of a larger framework that is itself eternal, with our observable patch just one small fluctuation in a timeless backdrop. The appeal of this view is that it sidesteps the problem of creation entirely. If the universe is eternal, you don't need to explain how it came from nothing, because it didn't. There was never nothing in the first place. Only the shifting forms of something. Philosophers going back to Aristotle have liked this idea for precisely that reason. They argued that nothing can come from nothing, so the universe or something like it must have always been here. Modern cosmology dresses that intuition in mathematics, but the core feeling is the same: reality doesn't need a beginning to be real. That said, the eternal universe hypothesis has its challenges. For one, our observations suggest that the universe is expanding, and that this expansion has been going on for about 13.8 billion years. If it had been expanding forever, it would look different, colder, emptier, perhaps too diffuse to form galaxies. This suggests that at least the current phase of expansion had a start. Eternal models get around this by proposing earlier phases, other epochs where the universe might have been contracting, static, or in a completely different configuration, before shifting into the mode we see today. There's also the question of entropy, the measure of disorder. If the universe has existed forever, why hasn't it already reached a state of maximum entropy, where nothing changes and no work can be done? Some versions of the eternal universe solve this by proposing ways that entropy could be reset or diluted, through cosmic bounces, the formation of new universes, or processes in which order can emerge from chaos in localized regions. Others argue that an infinite universe can contain infinite order alongside infinite disorder, so there's never a final state. When you think about it in the quiet of night, the eternal universe has a strange emotional pull. On the one hand, it robs you of the drama of a single world-defining beginning. On the other, it offers something more vast and serene. The idea that existence itself is the default, that reality never had to come into being because it was never absent. Your life, your planet, your galaxy are small eddies in a stream that has been flowing forever, with no source to trace and no mouth to empty into. It also shifts how you think about meaning. In a universe with a beginning, you can imagine a cause, a plan, perhaps even a purpose imposed from outside. In an eternal universe, there is no outside, only the endless unfolding of what already is. That unfolding might still have patterns, still produce beauty, still give rise to conscious beings who wonder about it. But it doesn't need a reason to happen. It happens because it cannot not happen. If this is true, then before the Big Bang is not a question of peering into a void. It's a question of peering into a past that stretches without limit. A past so deep that our finite minds can only grasp small fragments. And somewhere in that past, there were galaxies and stars and perhaps other beings asking the same question you're asking now, each convinced that their moment was the center of time, each a brief spark in a fire that never started and will never go out. Picture yourself sitting in a darkened room with a computer screen in front of you. For hours, the display has been black. Then, with a single keystroke, the screen floods with light and shapes and motion. A landscape appears, mountains, rivers, clouds drifting in a painted sky. It looks alive. It feels alive, but none of it existed a moment before the keystroke. All the complexity, all the apparent depth was generated from code, strings of instructions running in a system that existed long before the scene appeared. This is the kind of mental image the simulation hypothesis brings to cosmology, and when applied to the Big Bang, it offers a particularly unsettling twist. The moment of creation might have been less like the birth of space-time and more like the booting up of a program. The simulation hypothesis starts with a simple premise. If it's possible to simulate conscious beings with enough fidelity that they can't tell they're in a simulation, and if advanced civilizations have the capability and interest to run such simulations, then there could be vastly more simulated realities than base realities. In that case, the odds that we are in the base reality shrink, and the odds that we are in a simulation climb. Applied to cosmology, this raises the question: if our universe is simulated, what does that make the Big Bang? In this framework, the Big Bang could be the moment when our simulation began, not in a literal explosion, but as the initialization of the simulation's parameters, the constants of physics, the distribution of energy, the rules of quantum mechanics and gravity. From our perspective inside the system, this appears as a hot, dense, rapidly expanding universe. From outside, in the base reality, it might have been as mundane as pressing a button or running a script. Time within the simulation would start at that instant, but in the base reality there could have been billions of years or none at all before our start. This view reshapes before the Big Bang into something entirely different. It's not a physical state you could travel back into, but the computational substrate in which our simulated universe runs. The before is the realm of the simulators, the operating system, the hardware, whatever that even means in a context far removed from our physics. Just as the characters in a video game can't access the hard drive their world is stored on, we can't directly observe or interact with the base reality. It's tempting to dismiss this as pure speculation, but the simulation hypothesis has a peculiar way of dovetailing with certain mysteries in physics. For instance, our universe has a set of physical constants: the speed of light, the strength of gravity, the charge of the electron, that seem finely tuned to allow for the existence of stars, planets, and life. In a simulation framework, those constants could be simply the parameters chosen by the programmers to make a habitable, interesting, or stable simulation. The fine-tuning problem becomes less mysterious if someone or something selected the values intentionally. Another fit comes from the way quantum mechanics works. The probabilistic nature of quantum events and the apparent collapse of the wave function when observed can feel suspiciously like a system that renders detail only when needed, like a computer game that generates high-resolution textures only for the parts of the map the player can see. It's not that reality is faking it, but that it might be optimizing its resources. If the underlying computational power is finite, it would make sense not to calculate every particle's exact state unless some part of the simulation needs that information. This isn't proof, of course, and many physicists warn against drawing literal conclusions from these analogies, but the similarities are tantalizing, and they make the simulation hypothesis a compelling mental model for what before the Big Bang could mean. In this context, The Big Bang might be nothing more than the moment when the simulation clock started ticking, the moment zero of our in-world timeline. Before that moment, in simulation time, nothing existed. But in the base reality, the simulation's data and code could have been sitting on a server, or whatever counts as a server in that world, for an eternity. The unsettling part is that if this is true, there's no guarantee our simulation will run forever. The same way it could have been started, it could be stopped, paused, altered, or deleted entirely. The expansion of the universe, the formation of galaxies, the arc of human history could all be just one storyline among many, running for the amusement, study, or purposes of entities we can't perceive. The Big Bang would be their on switch, and the end, if it comes, would be their off switch. But there's also a curious comfort in this picture. If we are inside a simulation, then the before the Big Bang exists somewhere in some form. And it's not inaccessible because it's destroyed, it's inaccessible because it's outside our operating frame. There is something beyond our universe, something in which it's embedded, and that something might be as rich and strange compared to us as our world is compared to the pixelated landscapes of early video games. Thinking about this as you drift towards sleep, you might imagine the night sky as a vast screen, its stars glowing pixels, its galaxies swirling renderings. The Big Bang was when the system turned on, and every moment since has been the unfolding of code that was already written. Before that, in the realm outside the simulation, perhaps there were other programs running, other universes being tested or explored. Perhaps there still are. If that's the truth, then before the Big Bang isn't a time within our history. It's the environment in which our history was created, and though we may never touch it, the fact that our universe obeys consistent laws, runs on calculable rules, and carries the fingerprints of careful initialization may be the closest glimpse we ever get of the world beyond the code. Close your eyes and imagine a sheer, impassable wall. On one side of it is nothing. No light, no matter, no space, no time. On the other side is everything. The galaxies, the stars, the background hum of cosmic radiation, the soft arc of your own breath in this moment. The strange thing about quantum physics is that it says walls like this aren't always absolute. Particles can sometimes appear on the other side without ever climbing over or breaking through. They can tunnel across, simply showing up where classical physics says they shouldn't be. Now stretch that idea to its most audacious extreme, the universe itself tunneling into existence from nothing at all. In quantum mechanics, tunneling is a well-understood process. It happens because particles are described by wave functions which spread out over space rather than being fixed points. Even if a particle doesn't have enough classical energy to cross a barrier, its wave function still extends into the forbidden region. And if that extension is enough, there's a small but real chance the particle will appear on the other side. This happens all the time in the subatomic world, inside stars, inside semiconductors, even in the decay of atomic nuclei. The mathematics is clear, the experiments confirm it. Some cosmologists have wondered, could the universe itself have done something like this? Could reality in its entirety have tunneled from a state of nothing into being? The proposal is bold because it asks us to accept that nothing in this context is not just empty space, it's the absence of space, time, matter, and energy altogether. There's no where for the universe to be, no when for it to emerge into. And yet, in the quantum picture, this isn't a problem because quantum rules don't need a pre-existing stage. They can describe transitions between states even if one of those states has no space-time at all. In models developed by physicists like Alexander Vilenkin, nothing is treated as a kind of zero-energy baseline, a state where no classical geometry exists, but where the laws of quantum mechanics still hold. Those laws allow for a small but non-zero probability that a closed universe could spontaneously appear, fully formed, from this nothingness. Closed here means a universe that curves back on itself, finite in volume but without boundaries, like the surface of a sphere, but in 3 dimensions of space instead of 2. Once born, such a universe could begin expanding, its initial energy content setting the stage for all the structure to follow. If that expansion includes a brief period of inflation, driven by high-energy fields, then the tiny newborn universe could balloon to cosmic proportions in a fraction of a second, smoothing out any irregularities and giving rise to the vast, nearly uniform cosmos we observe today. In this picture, the Big Bang is simply the warm-up act after the tunneling event, the moment when the universe's contents shift from the exotic energy of inflation to the matter and radiation that will eventually form stars and galaxies. The unsettling part is that this doesn't require a cause in the traditional sense. Quantum tunneling is probabilistic, not deterministic. It doesn't ask why now, only what's the chance. Over an infinite timescale, even the most improbable event will eventually happen. If nothing is truly timeless, then it has all the time it needs, an odd phrase, since time doesn't exist there. But the point is that without a clock ticking, probability is free to act without a schedule. Eventually, the wave function describing nothing can fluctuate into something, and the universe exists. From our perspective inside the universe, this tunneling moment is the ultimate beginning. There's no hidden before to explore, because before there was no time, and without time, before has no meaning. The emergence of space-time is part of the tunneling itself. This makes the hypothesis uniquely satisfying for those who want a clean origin story, one that doesn't require an infinite regress of earlier states or a mysterious eternal backdrop. But there's a subtlety here. The nothing of quantum cosmology isn't quite the philosophical nothing of absolute non-existence. It's more like a state without classical properties, but still described by mathematical laws. Whether you consider that something is a matter of taste, critics argue that if the laws of physics exist in this nothingness, then it's not really nothing at all. It's a kind of invisible scaffolding. Proponents counter that these laws aren't physical things in themselves. They're just the rules describing what can and can't happen, and they don't need space or time to operate. From an emotional standpoint, quantum tunneling from nothing is a strange mix of austerity and wonder. It strips away the comforting idea of a pre-existing universe, or of a before that might be filled with other worlds or earlier epochs. It replaces it with a stark simplicity. There was no universe, and then there was, but it also offers a kind of quiet magic, because it says that the leap from nothing to something is not only possible, it might be inevitable. The universe didn't need a push from outside. It arose because in the quantum sense there was no barrier too high for it to eventually tunnel through. Lying in the dark, you might picture this origin not as an explosion but as a flicker, the sudden appearance of a tiny curved bubble of space-time, quivering with the energy of its own existence. In that first instant there is no outside, no void to expand into, only the bubble itself containing all that will ever be. It swells, accelerates, and in its swelling, it creates time. The ticking of the cosmic clock begins, and everything that follows, the birth of stars, the arc of civilizations, your own heartbeat, is part of the unfolding story that began when the universe tunneled into being. If that's the truth, then before the Big Bang is a question with no physical answer, because there was no before. The Big Bang was not a transformation of something that already existed. It was the first chapter, and the blank page before it wasn't paper at all, but the absence of paper, the absence of ink, the absence of the concept of a book, and yet, somehow, the book began to write itself. We are taught to think of time as a straight road. The past lies behind us, the future stretches ahead, and we move along the path in one direction, unable to turn back. The arrow of time feels absolute, enforced by memory and cause and effect. Yet physics in its colder language doesn't insist on such an arrow. The fundamental equations that describe how matter and energy behave work just as well in reverse. The distinction between before and after is something that emerges from the way the universe happens to be arranged, not an unbreakable law. And in that opening, some thinkers have dared to imagine a universe in which time is not a line at all, but a circle. To picture this, imagine walking around the Earth. You keep going forward, mile after mile, never hitting an edge. Eventually, without realizing it at first, you return to your starting point. The trip felt like a journey from here to there, but there was no ultimate destination, only a loop. Now apply that same geometry to time itself. Instead of beginning at a moment called the Big Bang and extending endlessly forward, time might curve back on itself, so far in the distance that the future eventually becomes the past, and the whole structure repeats. In such a model, before the Big Bang would simply be the far future of the universe, wrapped around to connect seamlessly with its beginning. The moment of creation and the moment of completion would be the same point on the loop, as indistinguishable as the north and south poles on a globe if you distort your perspective enough. The Big Bang then would not be the first moment, but one link in an endless chain that is also a closed circle. Some versions of this idea are purely geometric, imagining the shape of space-time as something finite and curved in the time dimension, as well as the space dimensions. Others have more physical mechanisms in mind, where the universe ages toward heat death or maximum entropy, and then, through processes we don't yet understand, transitions back into a state identical to its beginning. This doesn't necessarily mean the next cycle would be an exact replay. Just as walking around the Earth in a different season changes the weather you see, each journey around the loop could produce a new variation on the cosmic story. If time truly loops, then causality becomes a more intricate dance. Events could in principle be both causes and effects of themselves. A ripple in the early universe might be the echo of something that happened unimaginably far ahead in time, just as a decision you make now could send faint ripples backward into what you think of as the past. In most loop models, these paradoxes resolve because the loop is self-consistent. Every event fits into the pattern in such a way that no contradictions arise. It is less like a free-for-all and more like a perfect tapestry, where every thread crosses itself without tangling. This idea has been explored in various forms. Gödel's solutions to Einstein's equations, which allow closed time-like curves, certain cosmological models that envision cyclic boundary conditions, and even the more poetic suggestions that time's arrow is a byproduct of our limited perspective, inside a structure that from outside is perfectly symmetrical. In all of these, the Big Bang is not a unique origin, but a recurring point on a circuit that is forever traversed. From the standpoint of before the Big Bang, this is a radical shift. The before is no longer unreachable, it's right here, folded into the future. Every time you look forward to the farthest possible horizon, you are also looking, in some deep sense, at the past, the ultimate past. And if the loop is perfect, then the state of the universe just before the Big Bang is exactly the state of the universe just after its farthest future. The emotional weight of this view is complex. On one hand, it robs us of a linear narrative with a beginning and an end. There is no first cause, no moment when everything was new, no final chapter. On the other hand, it replaces that narrative with an eternal return, a cosmos that is forever self-renewing. In such a reality, nothing is truly lost. It will come around again, perhaps differently, perhaps exactly the same, depending on the details of the loop. You, your life, every sunrise you've ever seen could all be part of an infinite repetition. Whether that feels comforting or claustrophobic is a matter of temperament. Physically, time as a loop faces big challenges. Entropy, the tendency toward disorder, seems to push the universe in one irreversible direction. If time loops, something must reset the entropy at each pass, scrubbing the slate clean so the next cycle can begin in a low entropy state. Just as our universe appears to have begun, some speculative ideas propose mechanisms for this reset, perhaps tied to the fundamental nature of space-time or to processes in quantum gravity we don't yet understand. But as of now, no one knows if such a mechanism is possible. Still, the symmetry of the idea is irresistible. A linear timeline raises the question, why did it start? A loop has no such problem. It has always been. The cause of the Big Bang is the far future of the same universe, and the cause of that far future is the Big Bang, in an eternal embrace. It is an Ouroboros, the serpent eating its own tail, not in destruction but in sustenance. Lying in bed, you might picture time as a vast cosmic wheel, turning so slowly that to us it looks like a straight road. We are ants walking along its rim, unaware that each step forward is also a step toward the place we began. The Big Bang is one spoke on that wheel, and before is not somewhere else. It is the path we will one day take to arrive there again. If that's the truth, then the universe is neither young nor old, neither finite nor infinite in the way we normally mean those words. It is simply ongoing, forever circling, each pass through the loop, giving rise to new stars, new minds, new questions, and perhaps each time to someone lying in the dark, wondering what was there before the Big Bang. Imagine standing at the edge of a black hole, looking toward its event horizon, the invisible boundary where gravity becomes so intense that not even light can escape. To you from the outside, time slows to a crawl as anything approaches that horizon. To the falling object, though, the plunge is swift, inevitable, and irreversible. For decades, physicists have studied black holes as the strangest objects in the universe, regions where space and time are warped into forms that challenge our intuition. But a few bold thinkers have flipped the question around and asked, what if our entire universe is the inside of one of these? What if the Big Bang wasn't an explosion from nothing, but the birth of a space-time region on the far side of a black hole's horizon? At first, the idea sounds like a riddle. A black hole is supposed to be a dead end, a one-way trip into darkness. But general relativity doesn't forbid more exotic possibilities. In some solutions to Einstein's equations, the interior of a black hole doesn't just collapse to a singularity. Instead, it can connect to another region of space-time, a kind of bridge or white hole where matter and energy erupt outward. In these scenarios, the event horizon on one side is the point of no return for matter falling in, while on the other side, it's the point of emergence for a new expanding universe. If that's the case, then the before of our Big Bang could be the collapse of a massive star or perhaps an entire universe into a black hole in some larger parent cosmos. The core collapses under its own gravity, the densities rise beyond imagination, and instead of ending in a singularity where physics breaks down completely, the space-time inside curves into a new separate region. From our perspective inside that region, it looks like an expanding universe, hot, dense, and growing rapidly. To the outside observer in the parent universe, everything that fell in is hidden forever, frozen at the horizon. To us, the inside, that horizon is our Big Bang. This model does something interesting to the question of before. It doesn't say there was nothing. It says there was something else, something that existed in a space-time outside our own which we can never see or touch. That outside could have its own galaxies, its own history, perhaps even its own inhabitants, who have no idea they've spawned another universe by letting a star die in the wrong place. Black holes in our own universe might in turn be doing the same thing, forming new universes beyond their horizons. Each one could be a seed, its interior disconnected from ours, its physical constants perhaps slightly different from those in our own cosmos. If so, the multiverse could be growing in a branching tree-like pattern, with each universe giving birth to many more. There's a certain elegance to this picture. Black holes have always been mysterious sinks of matter and energy, swallowing information in a way that puzzles physicists. If each one is also a womb, then they aren't just the end points of stars, they're cosmic engines of creation. The singularity inside, instead of being an impossible point of infinite density, might be a bridge to another Big Bang. One of the strange consequences of this model is that the laws of physics in our universe could be influenced by the genetics of the parent universe. In some versions of the idea, universes that produce lots of black holes end up creating more offspring. So, over many generations, physical constants could evolve toward values that favor star formation and collapse. In this view, the fine-tuning we observe in our universe, the fact that stars live long enough for life to arise, that chemistry works the way it does, might not be an accident. It could be the result of a kind of cosmic natural selection, where universes that make more black holes leave more descendants. But as with most ideas about before the Big Bang, there's a catch. We can't observe the parent universe directly. Its light and signals can't cross the boundary of our Big Bang. The only evidence we could hope to find would be indirect, perhaps subtle imprints in the cosmic microwave background, or unexpected patterns in the distribution of galaxies that hint at conditions just before our horizon. So far, no such smoking gun has been found. Still, the black hole interior model offers a perspective that's hard to shake once you picture it. Imagine our entire observable universe. It's 93 billion light-years of galaxies compressed into a region smaller than an atom, hidden deep inside the gravity well of a star that collapsed long ago in a universe we will never see. From the outside, we would appear as nothing more than a silent, dark sphere hanging in space. From the inside, we feel infinite, with room for billions of galaxies and endless stretches of time. This vision can be humbling. It suggests that our reality is both immense and sheltered, vast and yet contained in something larger. The Big Bang in this telling is not the absolute beginning. It's the local start of our expansion, a new chapter in a story that began elsewhere. Before it, there was a different cosmos, governed perhaps by similar rules, perhaps by ones we can't imagine, and that cosmos, in turn, might have been born from the death of another. As you lie in the quiet and think about this, you might imagine the event horizon as a kind of curtain. On one side in the parent universe, it is the veil of an ending, a star collapsing, light and matter falling inward, never to return. On the other side, in ours, it is the curtain rising. The first instant of time, the flash of the Big Bang, the swelling fabric of space carrying galaxies outward. What looks like death from one vantage point is birth from another. If this is true, then every black hole in our sky is more than just a mystery. It is a potential universe in the making. Somewhere inside those dark spheres could be suns rising over alien worlds, oceans under strange skies, minds asking the same questions you are asking now. And they would never know that to us. Their entire cosmos is only the hidden heart of a black hole. The closer you get to the Big Bang in our equations, the more ordinary physics starts to fail you. The comforting framework of Einstein's general relativity, smooth space-time, curves defined by gravity, works beautifully for galaxies, stars, even the bending of light around black holes. But run it backwards far enough, compress the universe to a fraction of a second after its beginning, and the math starts to explode into infinities. The density goes infinite, the temperature goes infinite, and space-time itself collapses into a singularity where the rules dissolve. This is the point where physicists know they've reached the limit of their tools. To go further back to even begin to talk about before the Big Bang, we need something new. That something is what scientists call quantum gravity. Quantum gravity isn't one theory. It's a goal, a single framework that unifies quantum mechanics, which rules the small, and general relativity, which rules the large. The two are individually spectacularly successful, but they don't play well together. When you try to apply quantum rules to the fabric of space-time, you get contradictions. But without quantum gravity, we can't describe what happens when the universe is so small and so dense that quantum effects dominate the very structure of space and time. That's exactly the situation near or before the Big Bang. Several candidates have been proposed for a quantum theory of gravity, and each offers a different vision of what might have happened before our universe began. Loop quantum gravity, for example, suggests that space-time isn't continuous like a sheet of paper, but is made up of discrete chunks, tiny loops woven together into a kind of cosmic fabric. In this view, you can never squeeze space down to a true singularity, because there's a smallest possible unit of area and volume. Instead of collapsing into nothing, the universe reaches a minimum size and then rebounds. This quantum bounce replaces the singularity with a smooth transition from a contracting universe to an expanding one. Before the Big Bang, there could have been a big crunch of a previous universe which collapsed to a quantum-sized minimum and then bounced outward to become ours. String theory offers another route. In string theory, the fundamental building blocks of reality aren't point particles but tiny vibrating strings. Different vibrations correspond to different particles, and the theory naturally includes gravity when those vibrations ripple through space-time. Some versions of string theory suggest that our universe could be a three-dimensional brane floating in a higher dimensional space. Collisions between branes could trigger Big Bang-like events. In that scenario, before might have been another brane drifting through a higher dimensional bulk, waiting for the next collision to ignite a new expansion. There are also approaches that see time itself as emerging from deeper, timeless laws. In these, the Big Bang isn't so much the start of time as it is the moment when time became meaningful to beings like us. Before it, there could have been a timeless quantum state, something that can't be described in terms of before and after, only in terms of possibilities. From that timeless state, our universe might have crystallized into existence, carrying with it the flowing time we experience. What these theories share is the rejection of the singularity as the ultimate barrier. They all suggest that the Big Bang was not the absolute beginning, but a transitional phase between something else and the universe we see today. That something else could have been another universe, a timeless quantum foam, a higher dimensional arena, or a cycle of expansions and contractions. Quantum gravity also offers a subtle shift in perspective. If space and time themselves are subject to quantum uncertainty, then the idea of a clean, sharp moment when the universe began may be an illusion. Just as the position of a particle is smeared out into a probability cloud, the beginning of the universe might be smeared out into a range of possibilities, each with its own history. In that picture, the Big Bang is less like a single point and more like a fuzzy region in a larger map of possibilities. The challenge, of course, is that these ideas live at scales and energies far beyond what we can test directly. The Planck scale, the realm where quantum gravity becomes important, is so tiny and so energetic that no experiment we can build on Earth can reach it. Instead, physicists hunt for indirect clues, patterns in the cosmic microwave background, primordial gravitational waves, or tiny deviations from general relativity in extreme astrophysical environments. Each of these could serve as a fingerprint for a particular version of quantum gravity, hinting at the true story of the universe's earliest moments. For a listener lying in the dark, the quantum gravity view of before the Big Bang can be strangely comforting. It says there may have been something before, something structured, something lawful, even if those laws are strange to us. It removes the harsh edge of an absolute beginning, replacing it with a smoother, more continuous story where our universe is just one chapter in a much longer saga. You might imagine it like a river. From where you stand on the bank, the water seems to begin just upstream, bursting from a narrow gap in the rocks. That's your Big Bang. But if you could climb higher, you'd see that the river flows from a hidden valley, winding back through landscapes you can't see from here. The source isn't visible, but you know it exists because rivers don't just appear from nothing. In the same way, quantum gravity hints at hidden valleys of space-time that feed into our visible universe. And perhaps the most humbling thing about quantum gravity theories is that they don't just tell you what might have been before, they also remind you that the very concepts of before and after are part of the universe and might not survive intact when you leave it. In that sense, the Big Bang is not a wall to be climbed over, but the edge of the map beyond which the territory itself might be drawn differently. There's a certain romance to the word ekpyrotic. It comes from the ancient Greek ekpyrosis, meaning conflagration, a great burning of the world, followed by its renewal. The Stoic philosophers imagined the cosmos living through endless cycles of destruction and rebirth, each one ignited by a cosmic fire. In modern physics, the ekpyrotic model borrows the word, but replaces fire with geometry. Here, the Big Bang is not the beginning of everything, but the latest in a long series of collisions between vast, higher dimensional sheets of reality, what physicists call branes, short for membranes. To imagine it, picture two enormous invisible canvases floating parallel in a space you can't see, a fifth dimension beyond the three of space, and one of time we're familiar with. Our entire universe is painted on one of these brains. Everything you know, every atom and star and galaxy, is confined to it. The other brain is just as large, just as rich with its own contents, but completely separate, like two panes of glass with nothing in between except empty space in a higher dimension. These brains drift in this extra dimension, sometimes moving apart, sometimes sliding toward each other. In the ekpyrotic model, the Big Bang was the moment when our brain and another brain collided. The energy of that collision was immense, enough to heat our entire universe to billions of degrees, creating the hot, dense state we call the beginning. But here's the key. The brains don't annihilate each other in the collision. They bounce. They pass through one another, their energy spilling into both, and then they separate again. As they drift apart, our universe cools and expands, forming galaxies and stars. But eventually, over trillions upon trillions of years, they're drawn together again by forces in that higher dimensional space, setting up another collision, another burst of heat, another Big Bang. This means that before our Big Bang was simply the long cooling and spreading of a previous cycle. That cycle had its own galaxies, its own history, its own distant civilizations perhaps. It ended not in a total collapse, but in a slow, almost imperceptible approach toward another brain, until the two met and the whole story began again. There is no first cycle, only an eternal chain of them, stretching backward without end and forward without limit. The ekpyrotic model has some subtle advantages over other ideas. For one, it offers an alternative to inflation. The theory that our universe expanded faster than light in its earliest moments. Inflation is powerful and elegant, but it has its own puzzles: what started it, what stops it, and why it produces the universe we see. In the ekpyrotic picture, the smoothness and uniformity of the cosmos are not the result of an inflationary burst, but of the long, slow, pre-collision approach of the brains, which stretches out irregularities until they vanish. It also gives a natural answer to the entropy problem, the question of how each cycle can start fresh without being weighed down by the disorder of the previous one. In the ekpyrotic scenario, the expansion between cycles is so vast that all the debris and disorder of the old universe is diluted away, leaving each new Big Bang with a clean slate. But the model has its challenges. The idea of extra dimensions is difficult to test directly, and while string theory, the mathematical framework that often accompanies ekpyrotic cosmology, predicts them, we've yet to see conclusive evidence. The predictions of the ekpyrotic model for the cosmic microwave background, the afterglow of the Big Bang, differ in subtle ways from those of inflation. So far, the data fits inflation slightly better, though ekpyrotic cosmologists continue to refine their predictions. Even so, the ekpyrotic universe is a deeply evocative vision. Imagine looking up at the night sky, knowing that everything you see, every cluster of galaxies, is just one painting on a cosmic canvas. Somewhere, impossibly far away in another dimension, another canvas stretches just as wide, and every few trillion years these canvases meet and exchange a flash of energy that writes a new story in starlight. In the stillness of that thought, you might realize that this model erases the question, what was there before the Big Bang, in a way that feels almost gentle. There was always something before, another cycle, another collision, another era of cooling and drifting and quiet, before the next great meeting. The universe doesn't need to be wound up or lit from the outside. It has been moving through this dance forever. For us, inside the current cycle, the next collision is so far away that no human, no species, perhaps no star will survive to see it. But in the grand scheme, the collision is inevitable. The brains will drift toward each other again, and the impact will wipe away the old and make room for the new. And just as we cannot remember the last cycle, the beings of the next cycle will have no memory of us, only the faint structural fingerprints left in the way matter clumps and space expands. The ekpyrotic universe asks you to think of reality not as a single journey from birth to death, but as a rhythm, an endless heartbeat of collision and expansion. The Big Bang is just one beat in that rhythm, and it is not the loudest or the first. It is simply the one we happen to be living in. And somewhere in the space beyond space, the next beat is already on its way. You've probably heard the idea in passing, maybe in a late-night conversation or as a throwaway joke in a movie. What if we're living in a simulation? It's one of those notions that sounds at first like a philosophical game, a harmless what-if, something to amuse the mind on a quiet evening. But for some physicists, philosophers, and computer scientists, the simulation hypothesis is more than a playful thought. It's a serious contender in the list of possible answers to the question of what reality really is, and by extension, what might have existed before our Big Bang. The idea in its modern form was popularized by philosopher Nick Bostrom in the early 2000s, but it has roots that go back to Descartes' demon, Plato's cave, and countless myths about reality being an illusion. The basic argument is deceptively simple. If it is possible to create simulations of conscious beings, perfect immersive simulations indistinguishable from reality, and if advanced civilizations last long enough, then they might run enormous numbers of such simulations. If they run far more simulations than there are real universes, then statistically it's far more likely that you are inside a simulation than in base reality. In this view, the Big Bang was not the birth of matter and energy, but the initialization of a program. The laws of physics are the code, the speed of light, the strength of gravity, Planck's constant. These are parameters set in the simulation's engine. The quantum randomness we observe could be a feature of the system's processing, just as a video game might generate certain outcomes randomly to keep things varied. And the cosmic microwave background, the afterglow of the Big Bang, could be nothing more than the default state of the simulated environment before galaxies were rendered in. If this is true, then before the Big Bang is outside the simulation altogether. It is the world of the programmers, the operating system in which our reality is just one process running. That before might not resemble our universe in any way. Its dimensions, its matter, its sense of time could be completely different, and we would have no way to experience it directly, because our senses, our memories, and even our sense of self are all part of the simulation itself. Of course, there are objections. One is that just because something is possible in principle doesn't mean it's inevitable. Another is that we have no clear evidence of the simulation's edges. Yet some physicists point to strange features of the universe that they argue could be hints of a computational structure. The way space and time might be discrete at the smallest scales, the uncanny mathematical simplicity of certain physical laws, or the fact that the maximum amount of information in a region seems to be proportional to its surface area, as if reality is a hologram. If you imagine the simulation hypothesis as true, then the question, what came before the Big Bang, becomes an even stranger one. It's like a character in a novel asking about the author's childhood. The answer exists, but it's in a different frame of reality altogether. The programmers, or whatever beings are running the simulation, might not have anything like our form of existence. They might not even think of what they're doing as a simulation, in the sense we use the word. For them, starting our universe could be as simple and casual as us opening a new file. The simulation idea also forces you to reconsider the scale of reality. If simulations are possible and cheap enough to run, then there might be simulations within simulations, layers upon layers of reality stacked like Russian dolls. Our programmers might themselves be simulated by another civilization, which might be simulated by another, and so on, possibly without end. Each layer could have its own Big Bang, its own initialization point, triggered not by cosmic inflation but by the pressing of a button. In a strange way, the simulation hypothesis sidesteps the question of ultimate origins. If we are in a simulation, then the laws of our universe were chosen or coded by someone or something in another reality. But that reality has its own origins, which may or may not involve a Big Bang of its own. You can keep asking what came before at each layer, but unless you can reach the base reality, the one that isn't simulated, you'll never have the full answer. For some, this is unsettling. It reduces our grand universe with all its galaxies and history to a kind of elaborate artifact, an engineered system rather than a natural one. But for others, it's oddly comforting. In a simulation, nothing is truly lost. Every atom, every moment is data. In principle, the entire history of the universe could be replayed, examined, even altered. The programmers could back us up, restore us, run us again in different conditions. Immortality, in this context, is not a matter of life after death, it's a matter of being copied. Of course, if we are in a simulation, it might be running for a reason. We might be part of an experiment, a work of art, a historical reconstruction, or a test bed for physics. We might be entertainment. We might be an accident. And in each case, the before would be shaped by that purpose. Just as the before of a movie's first frame is not another scene, but the director calling for cameras to roll. For now, we have no way to confirm or disprove the simulation hypothesis definitively, but it remains an alluring answer to the question of what existed before our universe began. It suggests that the before is not part of space-time at all, but part of a different order of existence entirely. It might be unimaginably vast, unimaginably advanced, or unimaginably alien. And perhaps, just perhaps, someone there is watching the tiny glowing dots of our galaxies drift apart, smiling at the slow unfolding of a story they once set in motion.